रयते मधुन नव्या युगाचा मांस आता घडतो आहे. वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे. रयते मधुनी नव्या युगाचा माणूस आता घडतो आहे. वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे. रयते मधुनी नव्या युगाचा. कर्मवीरांचे ज्ञानपीठ हे शक्तिपीठ ही ठरते आहे. शाहू फुल्यांचे समानतेचे तत्वमानसी मूर्ते आहे. धर्मजातीच्या पादगांधींचे मूल्य मानवी जपतो आहे. रयते मधुनी नव्या युगाचा माणूस आता घडतो आहे. वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे. रयते मधुनी नव्या युगाचा. गरिबासाठी लेणी मोडून लक्ष्मी वहिनी झाली आई. कमवा आणि शिका मंत्र हा करुणाईला प्रेरक होई. स्वावलंबी वृत्ती ठेवून ज्ञान साधना करतो आहे. रयते मधुनी नव्या युगाचा माणूस आता घडतो आहे. वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे. रयते मधुनी नव्या युगाचा. दलितांसाठी अण्णा तुमची झिजली चंदन काया. अनाथ जीवा सदा लाभली मातृहृदयी तुमची माया. शून्यामधल्या नवसृष्टीचा निर्मिक तोही ठरतो आहे. रयते मधुनी नव्या युगाचा माणूस आता घडतो आहे. वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे. रयते मधुनी नव्या युगाचा. जीवनातला तिमिर जावा प्रबोधनाची पहाट व्हावी. इथे लाभले पंखले उनी उंच भरारी नभात घ्यावी. प्रतिभाशाली बहुजनांचा वेदू गगनी चढतो आहे. रयते मधुनी नव्या युगाचा माणूस आता घडतो आहे. वटवृक्षाच्या विशालतेचा मोहन भाला पडतो आहे. रयते मधुनी नव्या युगाचा.
Good morning to all the dignitaries, guests, and delegates. With great joy and immense exultation, I feel privileged to extend my warm welcome to all presented here for the second day of International Conference on Advances in Science and Technology. Now, I would request Dr. A.J. Dodmani sir, Assistant Professor, Department of Chemistry, to introduce today's chairperson.
Yes, thank you, ma'am. Am I audible?
Yes, sir.
Yes. Good morning, one and all. Myself, Dr. Anand Dodmani, Assistant Professor of Chemistry, Rajeshri Chhatrapati Shahu College, and the organizing secretary of this conference. It gives me an now the chief guest and the resource person, chairperson of this conference, all the delegates and all the members of this conference. Now it gives me a great pleasure to introduce the today's chairperson of this session, Dr. Machindra Gupnesar. Currently, he is working as an assistant professor of mathematics, Shivaji University, Kolhapur. Now, since he has completed his BSc, B.Ed, MSc in the Savitribai Phule University, Pune, and later he has qualified NET in mathematical sciences in the year 2001, and later he joined his PhD work and he completed his PhD in the year 2013 under the guidance of Professor Vilas Karat, Savitribai Phule University, Pune. As per his academic credential, he has 17 years of teaching experience, and as per his research concern, he has published 5 books and 3 book chapters, and he has completed more than 10 research articles in the national and international journals. He also life member of the Indian Mathematical Society, life member of the Shivaji University Mathematical Society, president of the Shivaji University Mathematical Society, member Board of Studies Mathematics, Shivaji University Kolhapur, member Board of Studies Tuljiram Chuturchand College, Baramati, and he is also the member of Board of Studies of Mathematics, Rajeshri Shahu Mahavidyalaya, Latur. Also, he is a member of Board of Studies of Mathematics, Mitras College of Girls, Pune. Now, he has also worked as a chairperson, invited chairman, organizing secretary, as well as convener of the various conferences organized by the Department of Mathematics, Shivaji University, Kolhapur. Now, I welcome Dr. Machindra Gupnesar and also take the charge of this first session of the second day of the conference. Thank you very much. Gupnesar, please.
Good morning to all. On behalf of Rajeshri Chhatrapati Shahu College, Kolhapur, I welcome Dr. Hoon Madam in the 2 days online international conference on advances in science and technology. I am very happy to introduce Dr. Yu Hoon Madam. Madam completed her PhD in November 2015. Madam has 6 years teaching experience and more than 9 years research experience. She published 34 research papers in reputed international journals. Mostly are in Scopus and SCI. 11 papers in proceeding, and she presented 17 papers in various conferences. Presently, she is working as a senior lecturer and coordinator of e-learning. With this brief introduction of today's speaker, I request Hoon Madam to deliver a talk on the control chart in process monitoring.
Welcome.
Madam.
I'm sorry, I forgot to mute my mic just now. Okay, thank you very much, Dr. Goffin and Dr. Suresh just now. So please allow me to share screen.
Yes, please.
All right. I see like I cannot share screen because disable participant to screen sharing. Yeah, Dr. Goffin, I'm sorry, I seem like I cannot share screen.
Now you can see her, madam.
Yes, now I can already. Thank you very much. All right, so I have shared the screen, so please let me know if you are unable to view my screen. Okay. So thank you very much, Dr. Goffin and also Dr. Suresh just now. And today, my name is Yu Hui Woon, and today I'm going to share with you about control chart in process monitoring. So we will start with introduction. Next, we will move to have a brief review on the control chart, and today we are going to focus in site-sensitive group run chart. Next, we will move to phase 1 and phase 2. Performance measure, numerical results, conclusion, and finally a list of reference. So introduction. So the first thing when we want to purchase a product or have a service will be the one we looking forward will be the quality. So therefore, quality has become a major business strategy. So a good quality product and also deliver a good service will have the advantage to dominate the market. So how can we ensure our product and service have a high quality? So in view of this, we need to have a process monitoring which is based on a continuous basis. So today we are going to use a control chart as a very useful process monitoring technique. So Shuhat chart is the first control chart to monitor and determine whether a process is in a desired state to produce product having acceptable quality. Here is an example of the Shuhat chart, which we have from Stuart et al. 1996. So as you can see here, how can we using a control chart to determine our process is capable to produce a quality product? We are going to compare and also monitor the process using the control limits. So we have three horizontal lines over here, which is the UCL, upper control limit, center line CL, lower control limit LCL over here. Okay, so next. We can see over here for the first 15 points, all the sample or the sample statistic is fall within the control limits over here, and we can see they are plotted randomly because they can be plotted above and also below the center line. However, a pattern observed when after the point 15 over here, where we can see there has an upward trend over here, and finally there is an out of control over here at our last point, which is point 25 over here. So this can see, using control chart, we are going to declare a process as out of control when our point or the sample mean sample statistic fall outside the control limit UCL and LCL over here. So it has been identified that Shuhat chart is low in detecting the process shift over here. So accordingly, our synthetic type control charts are suggested to increase the chart sensitivity. So a synthetic type control chart is a combination of the traditional Shuhat chart and a conforming run length CRL chart. So today we are going to monitor the process using the site-sensitive group runs SSGR chart. SSGR chart consists of two subcharts, which are the Shuhat subchart and also the CRL subchart. So here are the control limits for the Schuhart X-bar subchart. And for the CRL subchart, there is only one lower control limit, and we denoted using the J1, and it must be a positive value. It has been concluded that the SSGR chart is more efficient in comparison with Schuhart and also synthetic charts. So here is the list of the operation for our SSGR chart. So first of all, we are going to determine the LCL and UCL for our SSGR for the Schuhart X-bar subchart, and also the J1 for our CRL subchart. And as the name implies, it's site-sensitive group run. So it's important for us to locate where the sample mean or the location of the sample mean. So in view of this, we are going to let L equal to U equal to 0 over here. So since SSGR chart consists of two subcharts, which are the Schuhart X-bar and also the CRL subchart. So for the Schuhart X-bar subchart over here, we are going to take a sample of n observation and compute the X-bar. And then let's say the sample mean denoted as the X-bar sample mean over here fall within the control limit, then we assume the process is, we don't need to proceed to the CRL subchart. We can continue the process. However, if the sample mean is less than LCL, then we are going to compute L equal to L plus 1 and also reset U equal to 0. Or X-bar greater than UCL, we compute U equal to U plus 1 and reset L equal to 0. So as we can see here, both of the X-bar value is fall outside the LCL and also UCL. So in view of this, we only can say the sample over here is non-conforming. So we haven't declared an out of control yet. So when we are going to declare the out of control, we need to further determine using the CRL subchart. Okay, so we are going to use a CRL subchart to further determine whether the process is in control or out of control. So we move on. So we are going to compute the CRL value. So for the first CRL value, let's say the CRL value less than equal to J1, we are going to reset L equal to U and equal to 0, and we are going to signal an out of control. So bear in mind, every time that we signal an out of control, we are going to identify and remove the assignable causes here. So let's say the CRL value greater than J. So we are going to move on the process. Okay, we are going to have process monitoring as usual. So then next, for the second CRL value onwards, we need to have two CRL values, okay, to help us whether the process is in control or out of control. So in view of this, for the second CRL value, we will still move to the Schuhart X-bar subchart to go through the process monitoring. Then for the CRL value come from the third and onwards, we are going to check over here. So let's say the second and the third CRL value or two continuous CRL value, which R is equal to 2, 3, and onwards, they are in smaller and equal to our J1 lower control limit for our CRL subchart. Then both of the samples are fall within the same site, meaning that is either above the UCL, below the LCL or above the UCL. Then we are going to reset this value and then we signal an out of control. Then we are going to identify and remove the assignable causes. And finally, we are going to go back again for our process monitoring. Once we are so is everything all fine until here? Okay, so then if everything is okay, then we are going to move on. Okay, so right now we look into our CRL subchart over here. Okay, so this is a CRL value. So how we are going to determine our CRL value? So the white circle over here represent our conforming, then our black circle represent our non-conforming sample. So let's say, for example, over here is 1, 2, 3, 4. Okay, so we have 4 CRL values. Then the first CRL value is 4. Okay, then the second CRL value will be 1, 2, 3. So then the third CRL value is 1 and 2 over here. Okay, so let's say in this case, for example, we let our lower control limit CRL subchart has J1 equal to 3. Then, as we mentioned just now during our operation, the SSGR chart are going to signal an out of control when our first CRL value less than equal to 3 or for the second CRL value onwards, need to have two continuous less than equal to J1 and make sure the sample is at the same side of our control limit. So let's check. So for the first CRL value, as we can see here, the first CRL value is 4. So therefore, the SSGR chart will not signal an out of control here. So in view of this, because it's greater than 3, okay, so then the process was still ongoing, continue. Okay, so for the second CRL value, C is equal to 3, it is less than equal to 3. So however, we cannot declare this has out of control yet, because for the second onwards, okay, the CRL value, we need to have continuous 2. Okay, 2 CRL values. So we still continue the process. And then for the third CRL value, as we can see, is 2, is less than equal to 3. So in view of this, we can signal an out of control. With the condition, both of the non-conforming sample over here is fall in the same side in our Schuhart X-bar subchart. Okay, then we can signal an out of control. Otherwise, let's say one non-conforming sample is below LCL and then another one is above UCL, then we cannot signal an out of control yet. So next. Okay, so when we use our control chart in process monitoring, it involves 2 phases, okay, which is a phase 1 and also phase 2. So in phase 1, a set of process data is collected, so and analyzed to learn about the process. So constructing a trial's control limits, okay, to determine if the process has been in control over the period of time where the data were collected. So phase 1 also helps us to see if our control limit reliable to establish, okay, to monitor the future production. Okay. So in phase 1, Schuhart control chart is very effective because the chart is easy to construct and implement. So then after we already done the phase 1, we are going to move on to phase 2. A control chart is used to monitor the process by comparing the sample statistic or sample mean in our case for each successive sample as is drawn from the process to the control limit. So Schuhart chart is much less likely to be effective in phase 2 because the chart is less sensitive, okay, to small and moderate size process sheet. So where the quick detection is necessary. So therefore, in our sharing today, we are going to use our SSGR chart in our phase 2 process monitoring. Okay, so then we have the performance measure. So the performance measure of the control chart will influence the decision on the selection of a control chart. So the common performance measure is the average run length or the ARL. The performance of the control chart is usually studied using ARL. The computation of ARL requires us to determine the magnitude of shift. Right, okay. So then the practitioner may not know the exact shift size of the process in at once. So in view of this, if this is the case, we are going to use our expected average run length, EARL. Okay. So then, why we use the EARL? Because it does not require the practitioner to identify the shift size over here. Okay. So here we are going to go through an example. So a set of real data on the flow width measurement in microns for the hard bake process is adopted. So for the phase 1, we are going to apply 25 samples, each having size n equal to 5. Okay. So table 1 here shows the summary statistic of the phase 1 data. So as you can see here, we have a sample numbers. Then for each sample number, we have 5 observations. And then for each sample number over here, we are going to calculate the sample mean. And then we are going to find the range where we are going to use the maximum minus the minimum to obtain the range over here. Then finally, we are going to obtain the average mean. Okay. Then also we are going to find the average range over here. All right. So next, since as we go through just now, we can see in order for us to construct the control chart, we need the control limits. So for the control limits, we need the mean and also standard deviation. So we are going to estimate the mean and standard deviation from our phase 1 here. So here will be the formula we use for our mean. And also for this standard deviation, we are going to use a range. And also the D2 is a constant and we obtain this value from statistical table. So from here, we are going to apply this mean and also standard deviation, help us to construct a Schuhart chart, the control limit for our phase 1. So this will be our Schuhart chart. And as we can see over here, all the sample mean over here is fall within the UCL and LCL. And as we can see over here, the points are all plotted randomly. So we can assume the process is stable, and we can use the mean and standard deviation for our phase 2 to construct the control limit for the SSGR. So next, we move on. This will be the phase 2, the summary statistic. Okay, we use for the phase 2 data for the SSGR chart. So in phase 2, we are going to apply 20 sample number, and similarly, each sample number having 5 observations. And for each observation, we are going to calculate the sample mean, and this will be our sample statistic over here. Next. A fundamental assumption is that the magnitude of the shift side is assumed known. All right. So in real application, it's common for the practitioner that the shift side for the net shift in the process is unknown. So in light of this, it's important to consider for an overall range of the shift over here, which is the delta mean and also delta max. Okay. So where the delta mean and delta max represent the lower and upper bound of the mean shift respectively. Okay. So for this phase 2, we are going to have 2 scenarios. One is when we look into an overall range shift, okay, which is we take into account delta mean and also delta max. And after this, we are going to look into account where we only take into account only a particular shift. So here is an example where we take the sample size n equal to 5, delta mean 0.2. Delta max 1.0, our average run length in control is 370.4, and here will be the K and the J1 value. So from the mean and standard deviation we obtain from the phase 1, we are going to apply in our Schuhart X bar subchart for the control limits here, which is the LCL and also UCL. So we substitute accordingly, which is our K value here is 2.21. And the sample size equal to 5. And this mu naught and the estimate mu naught and estimate sigma naught we obtain from our phase 1. So next we move to our UCL. Okay, so similarly we substitute accordingly, and this will be our LCL and this will be our UCL. Okay, so over here our J1 is our lower control limit for our CRL subchart. Okay, because SSGR chart consists of 2 subcharts. So here we have a Schuhart subchart for the SSGR chart. So this is the upper control limit and also a lower control limit and also the CL, the center line values. Okay, we have. So as we can see here, the points or the sample mean or the sample statistic is within our control limits LCL and UCL until at the sample mean or sample 14 over here. So this is non-conforming. Okay, so if we are using the SSGR chart, we are not going to declare out of control based on SSGR. We are going to refer to the conforming run length chart as well to further determine the process, the status of the process. So this is a non-conforming sample. So we are going to refer to the CRL subchart. Okay, so this is our first CRL value. As we can count over here, this will be the sample 14. Okay, this is a CRL one. Okay, the sample mean 14 over here. This is a 14 sample. So therefore, our first CRL value is 14. All right. Okay, so then. So for the SSGR chart, okay, we are going to signal an out of control is either the first CRL value less than equal to J1. Okay, so we are going to check over here. So if you still remember, okay, for our lower control limit before this is 23. Okay, as you can observe over here. Okay, lower control limit is equal to 23. So if this is the case, we can see it is out of control. We are able to declare out of control at sample 14 over here. Okay, then we have our second non-conforming sample, which is over here, 1 and 2. So our second CRL value will equal to 2 over here. All right, okay. Then as we know, for the second CRL value, we need to have 2 continuous, okay? And please make sure the sample mean over here or the sample statistic fall within the same side. So for our case over here, we can see all the non-conforming sample is at the same side of the UCL, meaning that all the non-conforming sample is above the UCL over here, all right? So then this second CRL value, although it is less than equal to our lower control limit, we haven't can declare an out of control yet. Okay, so we need to wait for another one CRL value and fulfill the values less than equal to J1 over here. So we can see our third CRL value is over here, 1 and 2. So in view of this is less than equal to J1, and since two continuous values, okay, is less than J1 or 23 over here, and both of the points or the sample mean sample statistic are at the same side, okay, of the UCL over here, okay, the non-conforming sample. Therefore, we can declare an out of control at this third CRL as well. Okay, then next, okay, so we have the number 4, okay, CRL over here. So similarly is 1, 2. Okay, so in view of this is also less than equal to J1, which is 23 over here. Okay, so indirectly, actually, this is already another, this is the points, meaning that if we are using the SSGR, it will signal an out of control as the first CRL, third CRL, and also fourth CRL over here. All right, okay, so this is all the non-conforming sample based on our Schuhart subchart here. So next. So practitioner may not have historical knowledge, okay, to determine the exact shift site in the process. So in view of this, practitioner or we as a user, we consider a particular shift site of the process and use it corresponding control limits. The process monitoring will be affected if a different shift site actually occurs in reality. So we are going to move on to an example. Before this, we consider a range of the shift, which is delta mean 0.2 to delta max 1.0. And today we move on to check. Let's say today we determine based on our one particular shift site, which is our delta over here, which is equal to 0.6. Okay, meaning that we just consider a particular shift site 0.6, and we need to make sure the process is going to detect this shift site. So let's say shift site less than 0.6 or greater than 0.6, then the process is unable to determine or detect. So in comparison to the delta mean and delta max just now from 0.2 to 1.0, meaning that any process shift site occur within this range, the control check is able to detect during the process monitoring. Okay, so then similarly, we remain the same for the sample size n equal to 5. ARL not similarly 370.4. And our SSGR chart, this is the constant for our Schuhart X bar chart. And this one, the J1 is our lower control limit for the CRL subchart. So this is 2 and 9. So similarly, we are going to substitute it in our lower control limit and upper control limit using the formula. Okay, so this will be the formula we have. The estimate mu0 and estimate standard deviation we obtain from our phase 1. So after this will be our K. Okay, we are going to substitute 2 over here, and our N will be our sample size 5 over here. Okay, so we can substitute accordingly, and we can try to calculate the LCL. Okay, and also similarly for the UCL, upper control limit, similarly we are going to substitute accordingly. And we can have this lower control limit and also upper control limit over here. Okay, so the lower control limit will be 1.3807 and upper control limit will be 1.6305. Okay, so similarly, our center line is still remain the same. Okay, which is 1.5056. Okay, but the difference will be at our lower control limit and also the K value. Okay, so then similarly, we move on to our process monitoring using our Schuhart subchart for the SSGR chart. So this is the upper control limit, lower control limit, center line. So similarly, all the points over here are denote non-conforming sample. Okay, because if we are using the SSGR chart, it's just signal that is a non-conforming sample where we need to pay extra attention on it. So therefore, we use our CRL subchart to further determine the status of the process. Okay, so and as we can, as the name implies over here is a site sensitive group, right? So we need to make sure all the non-conforming sample fall in the same site. So let's say today the first, the second and the third is over here, second CRL value and third CRL value, then we cannot declare out of control, okay? But for our case over here, all the non-conforming sample fall above the UCL. Okay, so that should be no problem. Let's say we are going to check on the status of the process. So next, okay. Similarly, our first CRL value is happen at 40. Okay, meaning that's the non-conforming sample is happen in 40. Okay, so for your information, we are using the same phase 2 data. Okay, for the sample mean or the sample statistic. Okay, so similarly for our first CRL value, we can SSGR chart can signal out of control when it is less than or equal to the J1 here. Right. Okay, so the J1 over here is if you still remember, over here is 9. Okay, the J1 over here is 9. So in view of this, in our case, we can see that this value is greater than 9. Okay, meaning that our first CRL value 14 is greater than 9 over here. So we are not able to declare out of control at sample 14 here. So we are going to continue to monitor the process. So for the second CRL over here, it will be 1. Okay, so the second CRL value will be equal to 1. So this is less than 9 over here. However, we cannot declare an out of control yet, okay? Because both of these values fall either above the UCL or below the LCL. We need to wait until the third CRL value for R equal to 2, 3, and onwards. Then only we can declare an out of control here. So in view of this, we are going to wait, okay, and continue the process, okay, and then this will be, as you can see, this is a third non-conforming sample, okay. Why this is a non-conforming sample? Because it plot above the UCL over here. So in view of this, and at the same time, it is less than our J1 or lower control limit CRL. So if this is the case, we can signal an out of control over here. So if we signal an out of control over here, this is sample 14, 15, and 16. This is sample 16, meaning that the first out of control, meaning that the first out of control are declared at sample 16 over here. Okay, compared to when we monitor the process using a range of shift where the sample or the process declared out of control at sample 14. So next we have the number 4. CRL values will be 1, 2. So our number 4 CRL value will be 2 and less than equal to 9. And if you have these are continuous 2 samples, okay, or the 2 CRL value, then we are going to declare out of control. Okay, so for number 5, okay, is 1. Similarly, for our 6 CRL value is also 1 here. Okay, so in view of this, both of them are less than equal to 9. And this case, so we are able to declare an out of control. So always remember, when we declare out of control, meaning that we are going to identify and remove any assignable causes before we can resume our process monitoring again. So next. So conclusion, in this application, the SSGR chart declares the process has out of control. The first non-conforming samples occur at sample 14, and as we can see when we monitor using a range of shift, the first out of control signal issue at sample 14. So in view of this, corrective action are taken to identify and eliminate any assignable causes. So note that other non-conforming samples occurs at sample 16, 18, and also 20. Okay. So, however, out of control signals only declare at samples 18 and 20. Okay, so why it is so? Because as we know, when we have the conforming run length, CRL values for R equal to 2, 3, and onwards, we need 2 continuous values, okay, to be at less than equal to the lower control limit of CRL. And please make sure at the same time, as the name implies over here, we will look into where the location the sample mean fall in. Okay, whether if both of them are above the UCL or below the LCL. So here's the list of reference that we use in this study, and that's all for my sharing. Thank you very much of your time, and thank you very much of your attention.
Hello.
Hi.
Are there any questions from the audience? Hello.
Yes, I can see you. I
Are
can
there
hear.
any questions? So there are no questions from the audience. Madam have explained very nicely each and every concept related to control chart and process monitoring by giving simple examples. This talk is very informative. This talk will be very much beneficial to our researchers. Thank you, madam, for nice talk and being with us for this conference. We expect such coordination and support in future also. Once again, I thank you to madam.
Thank you, Dr. Gaffron, and thank you all the attention and the time from every one of you. Thank you very much.
Thank you very much, Dr. Woon, madam, and thank you very much, Dr. M.T. Gupnesar. Now, to deliver the vote of thanks, I invite Dr. T.S. Purne, madam, the assistant professor from Department of Statistics.
Thank you, madam. First of all, I would like to thank the resource person for this session, Dr. Yu Wei Un ma'am, the senior lecturer and e-learning coordinator. She accepted our invitation by the first talk. She shared this recent review of the topic on control chart in the process monitoring. We have the chairpersons, Dr. M.T. Gupnesar, assistant professors in Department of Mathematics, Shivaji University, Kolhapur. I thank him from the bottom of heart who has actively present for this session. Thank you, ma'am. Thank you, sir.
Thank you, Dr. Teswai.
Thank you.
And thank you,
Thank
Dr.
you.
Thank you.
Thank you.
Thank you, ma'am. Now, I invite Dr. A.R. Patil from the Department of Physics to introduce our next chairperson.
Just a minute, ma'am. Rajpuri sir is trying to join.
Hello.
Hello, sir.
Hello.
Hello, sir. Good morning, sir.
Good morning. बोला madam बोला.
Sir, just a minute. Mahesh has not joined.
आलेलं नाही का?
Hello, good morning, Rajpuri sir.
Sir, नमस्कार. बोला की.
Please go through your WhatsApp and see the message.
No, I have received the biodata.
हे सूर्यवंशींचे पाठवले वा ते प्रिंट घ्या WhatsApp पडदिशी.
Okay.
मध्ये एक 4 लाईन ड्रॉप करा.
हो.
Just a minute, sir. He's trying to join. Okay.
Archana madam, hello.
Hello.
I think he's joined now.
Yes, sir. Yes, sir. He joined now. Let's start, sir. Good morning, all of you. It gives me immense pleasure to introduce Chairperson for this session, Professor K.Y. Rajpure, sir. He is currently working as an assistant professor and head. Sorry, he is currently working as a professor, and head in the Department of Physics of Shivaji University, Kolhapur. He completed BSc degree at Raj Shikshan Sanstha Science College, Lonan in 1992 with university first rank. He completed his MSc in 1994 and secured the first rank in Shivaji University. After MSc, he had chosen research as a means for career development. In 2000, he was awarded a PhD degree in physics for research in semiconductor spectrum storage cell. Under the guidance of Professor C.H. Gupnesar, he has qualified SET exam in physical sciences in 2002. Though his research was started with storage cells, by the time he spread his wings in various research areas, his later research areas include solar cells, transparent conducting oxides, photoelectrochemistry, and gas sensor. He's been an expert in photoelectrocatalysis. The honor of starting photodetector research in Shivaji University is to his credit. Currently, he is working on an electronic memory devices, namely Memorister also. Till now, he has published more than 220 research articles in international journals and received over 8,801 citations with H-index 57. He successfully guided 14 PhDs and 2 MPhil students. Currently, 7 PhD scholars are working under his guidance. He published 5 books and filed 2 patents. He completed 5 research projects with worth 86 lakh rupees. He has worked as head of UC, CFC and coordinator of DST SEP Kolhapur Center for 4.5 years. He was instrumental in procuring modern sophisticated analytical facilities at the center. He is the chairman of the Board of Studies in Physics and a member of the Academic Council of Shivaji University. He is a member of BOS in various institutes, namely Karnataka University, Dharwad University, JSPM's Rajarshi Shahu College of Engineering, Tatode Pune, TC College Baramati, Walchand College of Engineering Sangli, Vivekanand College Kolhapur, KBP College Pandharpur, DKT Ichalkaranji, and so many are there. Recently, a feather of international recognition has been added to his crown. Experts from Stanford University, USA published a list of top 2% of scientists from all over the globe. He has been placed in the top 2% of world scientists in material research. He was recently honored with the Brand Kolhapur Award for being ranked in the top 2% of the world. With this brief introduction, I request to Professor Rajpure sir to chair this session.
Thank you, Dr. Patil. Good morning, one and all, especially my colleague and friend, Professor Killedar. Today's guest, Dr. Mahesh. Mahesh, am I audible?
Yes, sir.
Okay. So I'm greatly honored to have chairmanship of this session for the lecture by one of our alumni, Dr. Mahesh Suryavanshi. Right now, he is in Australia. So I am very much thankful to Rayat Shikshan Sanstha and the authorities of Rajarshi Shahu College, Kolhapur, to interest me this opportunity. So to begin with, let me introduce first the today's speaker. He is our product. He is product of Shivaji University, Kolhapur. He is product of Department of Physics. So Dr. Mahesh Suryavanshi, right now he is working as a ARC DECRA fellow and lecturer at the New South Wales University of New South Wales in Australia. He has completed his bachelor's and master's degree in Shivaji University, Kolhapur, particularly, as I told, he did his MSc in Department of Physics, and he completed his PhD in 2015 at Department of Physics, Shivaji University, Kolhapur. Then he shifted to Chennom National University, South Korea, to work as a research associate. He worked there for 1 year, and then he worked in the same Chennom National University as the Brain Korea postdoctoral fellow for next 3 years. And since 2019, he shifted to Australia, and he is working at various positions in the University of New South Wales as a postdoctoral fellow. He is a group leader for multifunctional nanomaterials and device research group. He is, as I told, he is a ARC DECRA fellow, and he is working as a lecturer since this year, I think, in University of New South Wales. He has many recognitions to his credit, and list is in front of me, but I would like to highlight the research interest in which he is working. Particularly, he worked on chalcogenide solar cells, nanocrystalline solar cells, or nanocrystalline thin film for solar energy conversion. Right now, he is working on perovskite nanocrystalline materials for solar energy conversion, and he is using metal oxides, transition metal oxides, hydroxides, phosphides, and other nitrites for the electrocatalysis. He was instrumental in getting various grants. Particularly, he was awarded with the ARC DECRA fellow. Then he received Early Career Research Award of Spain and European Commission. Then he received the grant of a National Research Foundation project in South Korea. Then Korea Research Foundation project also was received to him. He has, as I told, he has received many awards, and he has achieved great success, excellence as far as research in material science is concerned. I would not list out the various awards he has received, but I would like to highlight the thing that he has more than 90 publications which are of international repute, or the papers he has published in the journals of international repute, whose impact factor is very high. In many cases, the impact factor is more than 10. And he has one book to his credit and 2 book chapters. He has delivered more than 10 invited talks, keynote addresses, and the total citations to the publications by Dr. Mahesh Suryavanshi, they are more than 3,000. And H index of his publication is approaching to 32. So such a eminent researcher is amongst us, and he will be delivering the topic of his interest soon. So I take this opportunity to invite Dr. Mahesh Suryavanshi to deliver his talk. Over to you, Mahesh.
Thank you so much, sir, for such a nice introduction. So I will start my presentation. Give me a minute just to upload my presentation here. Yeah. Okay. So good afternoon, everyone. Of course, it's afternoon here. Good morning to all of you guys. So my name is Mahesh Suryavanshi, and I'm working as a DECRA fellow and lecturer at UNSW at the School of Photovoltaic and Renewable Energy Engineering. First of all, I would like to thank Rajesh Chhatrapati Shahu College and the conference organizing team for giving me an opportunity to speak on such excellent topic, which is also an important topic considering the need of renewable energy sources. Before I actually proceed further for my presentation, I would like to briefly explain about my research activities, what we are doing in my group. So my group's research interests are mainly in the development of new earth abundant and non-toxic compounds for use in energy devices such as thin film solar cells, solar windows, and renewable hydrogen production using scalable approaches. Today I will, of course, today I will mainly talk about the pathways to the green hydrogen production and our contribution to it through the use of different earth abundant materials and their scalable methods. So, all right, let's go ahead and get started. So before I actually start my presentation, let me briefly tell you about my university. So UNSW has been established in 1949 and it ranks 43 in 2022 QS World Ranking, and it ranks 6th in Australia and 1st in Australia for engineering and technology. So we have 9 different faculties, including engineering and sciences, and each faculty has again different several schools in it. Our school, that is School of Photovoltaic and Renewable Energy Engineering, is one of the top schools in the world, and it is well recognized for its research in solar cell, or we can say photovoltaics. Of course, it is also quite famous in when it comes to the renewable energy technologies and their techno-economic analysis and so many other things. We have a state-of-art facilities for fabricating the high-efficiency solar cell, which includes the commercially available silicon solar cells, as well as thin film solar cell, and recently a perovskite solar cell. We also hold the world record efficiencies for all these 3 types of solar cell technologies. So this is all about UNSW. So let's get started with my presentation today. We all know that our aggressive use of fossil fuels is responsible for increasing CO2 emission, which is accelerating the climate change and hence threatening the natural ecological balance as a consequences of the global warming. Therefore, we must find suitable alternative energy sources that are sustainable and those who resolves the issues associated with the use of non-renewable energy sources such as fossil fuels. So this picture is quite clear, and of course I don't need to explain it in detail because this is a kind of a very hot topic, and everybody knows about what are the changes happening around us due to this global warming, and again which is due to the excessive use of these fossil fuels. So among the different renewable energy sources, we know that the solar energy is world's most abundant energy sources. So a brief view of the different energy resources available on Earth, as shown in this picture, which demonstrate the dominant position of the solar energy among all renewable and non-renewable energy sources. The total sum of the recoverable energy from all the reserves is around just 1% of the solar energy that is supplied to the Earth's surface by the sun. Moreover, the solar energy supplied to the total surface of the Earth, that is including the land and water, is nearly 9,600 times larger than today's total energy consumption of the world, which is about 17.91 terawatt in 2020. And this is a rough value, not exact value. We also know that this enough sunlight reaches the Earth's surface, or we can say reaches to us every 15 minutes to power the world for an entire year. In addition, the solar energy or the sunlight, let's say solar energy, it's a safe and clean solar energy which powers homes, businesses, and the power plants everywhere. However, even though the solar energy is much more than enough to meet all our energy needs for the lifetime of the solar system, but the challenges that lies in the development of economically viable technologies for its harnessing, storage, and utilizations. So how we can harness this solar energy? So this solar energy can be utilized or can be harvested directly or indirectly in a variety of aspects, such as using the solar thermal plants, as well as the photovoltaics or solar heating systems, and finally your solar fuels. So solar thermal plants involves the harnessing of solar power for practical applications, from solar heating to electrical power generation. The solar thermal collectors, such as the solar hot water panels that we can we can see on our houses, just to heat water, which I assume everyone is aware of, are commonly used to generate solar hot water for domestic as well as the light industrial applications. Today, the PV represents the most widely disseminated technology and is one of the fastest growing industries in the world. So this PV technology usually employs this solar cell, or we can say like solar PV arrays, to convert the energy from the sun into the electricity, which has been an intrinsically difficult in terms of the storage, considering the intermittent nature of solar energy. Solar energy is not available all the times, because like we can only the sunlight is only accessible in the daytime. Of course, it is not even accessible on a cloudy days or during the rainy season. So converting the solar energy into easily storable chemical energy or a fuel has emerged as an ideal option for solar energy utilizations. Considering the intermittent nature, or like let's say among these different potential solar fuels, we can say like hydrogen generated from the solar water splitting or electrolysis, which is also called as this artificial photosynthesis, has received tremendous attention recently as most promising fuel, especially for powering fuel vehicles. Of course, there are so many other different applications of this hydrogen that is generated using the electrolysis or artificial photosynthesis. So what is this actually artificial photosynthesis? Of course, this artificial photosynthesis is that's what I'm going to talk from in my whole next few slides or during my whole presentation. So this artificial photosynthesis is a way of mimicking the natural synthesis process that plant uses to create the energy from sunlight, carbon dioxide, and the water. So it is actually a chemical process that converts the water and CO2 into oxygen and hydrogen and carbohydrates respectively. So this term artificial photosynthesis is commonly used to refer any scheme for capturing and storing the energy from a sunlight in the chemical bonds of fuel, that is also called as solar fuel or simply hydrogen. So this solar or photoelectrochemical water splitting converts the water into hydrogen and oxygen, where the hydrogen is a valuable product. Of course, the oxygen, we shouldn't say like it is not a valuable product. Of course, we need oxygen to live, but let's say like here, when we split the water, hydrogen is much more valuable than the oxygen, and which is a major research topic of this artificial photosynthesis recently. So let's see like why we need hydrogen and what is actually a green hydrogen, which is the title of my today's presentation. So like why we need hydrogen. We all know that the hydrogen is abundant, clean, and efficient, and which can be derived by various means from a chemical compound such as water and ammonia. So like this schematic schematics presents the different ways to produce this hydrogen, either by renewable energy sources or using the traditional sources, just by simply burning this natural gas and the coals. So one of the most common ways to extract the hydrogen is with the device called as electrolyzer, which passes an electrical current through the water, splitting apart hydrogen and oxygen atoms, which I will show again in the next slides, where I will briefly explain how this actually electrolyzer or photoelectrolysis cell works. So so the hydrogen and oxygen gases, those which we have split from this electrolyzer, then can be stored as gases for various uses. The hydrogen is the energy, again, like in addition, this hydrogen is an energy storage medium, similar or just like a battery, but unlike batteries, which eventually lose their ability to hold a storage or a charge, or this hydrogen gas can be stored indefinitely. That means simply like we all know that like we have a cell phones and we have a battery in it. So after like particular use, let's say after using a cell phone for one day, we have to recharge it. But that's not the case with the hydrogen gas. that means like we can simply store this hydrogen gas indefinitely, and then we can use it as per our choices or as per our like different applications. So perhaps the base argument in the hydrogen's favor is that when we burn this hydrogen, or simply when we combust this hydrogen for a heat or passed through a fuel cell to make the electricity or to run a car, the only byproduct that we get is chemically pure water. That's because it's H2, and when it reacts with the O, it usually forms the H2O. So that's the one very big advantage, and that's why I said it's perhaps the base arguments in the hydrogen's favor. In addition, this hydrogen can reduce, of course, the energy dependence as well as the reduced pollution by reducing the carbon dioxide emissions in the atmosphere. Why I'm saying that, like, it will help us to reduce the energy dependence as well as to reduce the pollution, because like from this like schematic, we can say, as I told you, so the hydrogen can be produced from this renewable energy as well as by simply burning the natural gas and the coals. So when we produce the hydrogen using these traditional ways of burning natural gas and the coals, there is a like excessive emission of the carbon dioxide in the atmosphere, and that is the reason why the people are searching for renewable energy approaches to produce this hydrogen. As well as we are, I mean, like it's not only about the hydrogen. We are also working on like developing the different renewable energy sources. Let's say an example of photovoltaics as well. But let's not talk about the PV today, because like mainly the today's topic of the presentation is all about the hydrogen. So what is actually a green hydrogen? There are different types of like hydrogen. Of course, I can't say like a different type of hydrogens, but like this hydrogen is often like associated with its color, whether it's like a gray, blue, or green. So that's the reason like I said like what is a green hydrogen, which I will explain like very shortly. So these actually colors of this hydrogen represents a key distinctions or the differences in the emission profiles for the various ways the hydrogen is produced. So this gray hydrogen, which is of course like which is produced by burning simply coal and oil, that contributes a lot to the carbon dioxide emissions. Similarly, the blue hydrogen also contributes to the also significantly contributes to the carbon dioxide emissions in the atmosphere. That's because the blue hydrogen is also produced from the natural by simply burning the natural gas. Whereas this green hydrogen, which is only about 4% for now, which is produced from the water electrolysis. And that's the reason like we are calling it as a green hydrogen. That's because let's say like we are producing this hydrogen by water electrolysis using the renewable energy sources. Again, I will explain it in detail in my next few slides. So what is actually this gray hydrogen? Let's talk a little bit about the how these colors can be like distinguished, or how the hydrogen can be distinguished based on their colors. So the gray hydrogen is typically produced from a natural gas in the process called as methane reformation, while this brown hydrogen is produced from a coal gasification. These are the most dominant and the cheap method of hydrogen production, but that accounts for the highest CO2 emissions in the atmosphere, just like I said a little ago. Whereas this blue hydrogen, which is usually produced using the fossil fuels, but usually dealt with the carbon capture storage. This blue hydrogen can be stepping stone of sorts to move away from a gray and the brown hydrogen. Of course, like I don't want to go into like a brown hydrogen, because there is a lot more to talk about the gray and brown hydrogen. So I will just skip that part. Of course, like you can get a lot of information about like how this gray hydrogen is produced on a Google. You simply search it on a Google, like a gray hydrogen and how the gray and the blue hydrogen is produced. Because like I will mainly talk about the green hydrogen today. So like so as I said, like this blue hydrogen can be a stepping stone of a sorts to move away from this gray and the brown hydrogen and move towards the green hydrogen technology or economy. So what is actually a green hydrogen? So the green hydrogen, as I said earlier, is produced using the renewable energy sources such as the solar, wind, or even geothermal plants via electrolysis of water. What exactly that means? So simply like so whatever the surplus electricity we get from the PV or the wind energy or geothermal plants, we can supply it to the water electrolyzer or water electrolysis cell, and then we produce the hydrogen. So this process is actually a clean, but of course, like it's currently very expensive, and that's the reason the production of the green hydrogen among this gray hydrogen and the blue hydrogen is just only about 4%. And the reason again is like the technology that is being developed to produce this green hydrogen using the renewable energy sources is very, very expensive at the moment. So, but again, the cost of these renewable energy sources, if you see recently, the cost of the silicon solar cell or the solar PV is drastically decreased. Okay, again, thanks to my school. Of course, not only my school. I should really thank to Professor Martin Green, who has made a significant contribution in the silicon solar cell, which is commercially available in the market now. And the reason the prices are going down, the prices of the silicon PV is going down. That's because we are now able to produce a silicon solar cell near we are now able to produce the efficiency of the silicon solar cell near to its theoretical limits, which is relatively at a lower cost. And hence the reason this process is getting much and more cost effective, or let's say simply cheap. So again, if this solar PV market is getting cheaper and cheaper every day, that means the production of this green hydrogen by simply using the PV electrolysis technology will be much more cheaper, and that will significantly contribute again in the production of this green hydrogen in near future. However, again, it's not only about these renewable energy sources that usually powers the water electrolysis cell, but again, there are some costs that are associated with the actual water electrolyzers, which is again a little bit expensive at this stage. That's because there is still a lot of research work that we need to do in trying to design an efficient water electrolyzer cell, let's say. So, and again, so that's the reason the contribution of the green hydrogen in currently is just 4%. So how this green hydrogen can be produced. So of course, there are again, there are different techniques, or let's say the approaches where we can, by which we can produce this green hydrogen. So let's say so these are the different approaches to produce this green hydrogen, such as direct solar, that is direct water splitting using the sunlight, and some semiconductor compounds. Again, we can also use the biomass to produce the hydrogen. Of course, this simply suggests this produced hydrogen from all these techniques can be stored as in terms of its use in later applications. So these two can be classified as a direct water, a direct hydrogen production system, whereas the solar PV, wind, and the geothermal can be considered as the indirect approaches to produce the hydrogen, because so we initially produce the electricity from these three approaches, and then we give that electricity to the electrolyzer, and then we produce the hydrogen. So of course, I will talk about mainly direct solar water splitting, a little bit about the biomass, and then of course I will explain a little bit about the solar PV assisted hydrogen production. So let's start with how this hydrogen is produced from the biomass. So actually the biomass gasification, I'm pretty sure even though I have also studied a little bit about this one when I was in my school, so I'm pretty much sure that everyone here in the today's session are all aware of how the hydrogen is produced from the biomass. So simply I will explain in a brief how this biomass gasification is a technology pathway that actually uses a control process which involves the heat, steam, and the oxygen to convert this biomass into hydrogen and other products without a combustion. We know that, of course, because of the growing biomass removes the carbon dioxide from the Earth atmosphere, the net carbon emissions of this method can be very low, especially if we couple with the carbon capture, utilization, and the storage when we consider it in the long term. The gasification is a process that converts actually organic or fossil-based carbon-based materials at a very high temperature, around 700 degrees centigrade, without combustion or with a control amount of oxygen, and on or steam into carbon monoxide, hydrogen, and carbon dioxide. This carbon monoxide then reacts with the water to form carbon dioxide and more hydrogen via the water gas phase shift reaction. Again, these again the absorbers or the special membranes that are used during this biomass gasification can separate the hydrogen from this gas stain. Probably should be in here, and this finally we can collect pure hydrogen and can be further stored for later uses. Okay, so this is a little bit about the how we can produce the hydrogen from the biomass. Now let's talk about how we can produce the hydrogen from different renewable energy sources, such as the solar PV, wind, and the geothermal. So this is actually an attractive method. I'm not going to talk a lot about the wind and geothermal. That's because it's not my expertise. I will mainly talk about the solar PV. But again, just simply consider we use these all three kinds of renewable energy sources to generate the electricity, and then we use this electricity to power the electrolyzer cells where the actual water splitting reaction happens, and we get the hydrogen at the cathode part and the oxygen at the anode part. So because currently I'm working with so the PV assisted electrolysis, or let's say PV driven water electrolysis, I will just focus on mainly talking about the solar PV. Of course, that's not again not in detail, because I will focus a lot on actual direct solar water splitting, which is called as the photoelectrochemical water splitting. So these are actually called as these are the attractive methods, which is currently a technological readiness level in between 4 to 6. So when I say technological readiness level, it's called as TRL, which is in the range of about 4 to 6. So that's mainly this electrolysis, which is powered by the solar PV. So when we say the technological readiness level, that means actually this technology is almost ready for the commercialization. And that's why I'm saying I will mainly talk about the solar assisted PV driven. That's because we are working on it, and we are almost near about to actually commercialize this technology here at UNSW. So what is this as I said, this energy in the form of electricity is used in an electrolyzer, which split the water into hydrogen and oxygen, and then hydrogen is usually stored under pressure in the storage tank, and then oxygen too is stored as it requires in the fuel cell process to electricity again. To produce the electricity again. It is important to note that hydrogen is not an energy source, but it's actually an energy carrier. Again, I'm not going to talk about it in detail. So this is all about PV, solar PV assisted or the wind or geothermal assisted electrolysis. Just a key lesson from this slide is that we use this renewable energy sources to produce the electricity. We all know that what is PV, what the PV does. We know that what the windmills does. We also know that what the geothermal plants does. So their main aim is to produce the electricity, and then we use this electricity to drive this water splitting reactions using the electrolysis and the produced hydrogen. And that's the reason we call it as a renewable hydrogen production, or let's say a green hydrogen production. That's because we are using all natural sources which are readily available for us to produce the electricity. That is sunlight, here wind, and here the water, and that's the reason it is called as the green hydrogen production or renewable hydrogen production. Now let's talk about what is a direct solar water splitting. So actually it is a most promising and attractive method to produce the hydrogen, which is also called as the PEC water splitting. Actually, a techno-economic analysis that has been done even at UNSW or even by other researchers all over the world, suggests that the PEC approach to generate the hydrogen can compete with actually a PV coupled electrolysis. So that means a PV coupled electrolysis, or even with the steam reforming methane, just like I explained in my earlier slides, if we can achieve some certain efficiency or the or the stability metrics. So let's talk about how the hydrogen is produced using this direct water splitting or PEC water splitting. So now from now on, I will mostly say it's a PEC water splitting, not a direct water splitting. That's because it's the same word, but when I say direct water splitting, that's usually for a general audience. So let's say from now onwards, it's a PEC water splitting. So what is this PEC water spreading? So actually, in a PEC water spreading process, the solar radiation is directly used to split the water. This can be like clearly understood, or can be clearly understand from this schematics. And this solar radiation is directly used to split the water into hydrogen and oxygen, and this process again is called as the PEC water spreading. So what we need to produce the hydrogen using the sunlight, so what actually we need is we need the semiconductor electrode materials that can absorb the sunlight and produce the electron hole pair, and then there is a separation of these electron hole pairs, and then either electrons or the holes will be utilized to drive these water splitting reactions. And then again, at the last, after driving this water splitting reaction, we'll get H2 gas on the cathode and the O2 gas on the anode. And then again, we can store this hydrogen for our later uses. So these semiconductor materials that we use in these PEC processes are similar to those which we usually use in a photovoltaic solar electricity generation, that is a photovoltaics. But for PEC application, the semiconductor is actually immersed in the water-based electrolytes, where the sunlight energizes the water splitting process. That's what I explained a little bit early a while ago. So let's talk about how this the PEC cell works. So when actually semiconductors, we usually shine a light on the semiconductor electrodes that absorbs the solar energy, and then there is a generation of the electron hole pairs in the semiconductors that can be either photoanode or the photocathode. So these photogenerated carriers can drive the reduction and the oxidation reactions if the charge injection into the reactants are thermodynamically favorable. So the reduction of water to the hydrogen should be on a photocathode side, and the oxidation of the redox mediators on the photoanode sides. Of course, these reactions occur simultaneously, and then there is a formation of the reduction of these oxidizes redox mediators and the oxidation of water to the oxygen on other photoelectrodes. In short, what happens is there is absorption of light near the surface of semiconductors that creates an electron hole pairs, and then the holes from that is a minority carriers actually dips to the surface of the semiconductors, that is a photoanode, where they react with the water to produce the oxygen, whereas the electrons are connected to the metal electrodes. Typically it's a platinum, but again it depends on what kind of system we are trying to build. If it's unassisted system, both based on the semiconductor electrodes, then there can be a different photocathodes as well, which I will explain, which we have actually developed in our lab, which I will explain in my some last slides. So these electrons are actually connected to the metal electrode. So for now, let's say platinum electrode, where they combine with the H+ ions in the electrolyte solution to make the hydrogen. And now finally, the transport of H+ ions from the anode, usually here, this transport of these H+ ions from the anode to the cathode through the electrolytes, which completes the this electrochemical circuit, or we can say which completes the overall reaction. So these are the equations on for example, let's say this is anodic reaction, which is also called as oxygen evolution reaction, which is a kinetically sluggish because it needs a relatively high potential of about 1.23 volt, which is a theoretical, but basically it requires the actual potential of about 1.4 to 1.6, depending again on the semiconductor photoelectrode materials or the catalyst. Whereas the cathodic reaction is usually called as HER. And again, of course, when we combine cathodic and anodic in one cell, that's the overall reaction. Again, you can read about this in detail if you want to actually go into more details about this chemical reactions that occurs in this PEC electrolysis cell on a Google, or there are so many books available. Okay, so how this since of course this PEC water splitting reaction requires the several different steps, or includes several different critical steps, such as the light absorption, charge separation, charge transport, and then surface chemical reaction, just like what I explained in these slides or from this schematic. We need high quality semiconductor materials that can sustain as well as perform very well in the electrolyte, aqueous electrolytes, to produce the hydrogen. So usually an ideal material that people think as a good photoelectrodes for carrying out these water splitting reactions should possess a suitable band gap to allow the light absorption and the electron excitations with a sufficient energy, usually like greater than 1.23 electron volt or equivalent to about 237 kilojoule per mole, without considering the over potential. The over potential, that means like theoretical value is 1.23 volt, but I said like in my last slides, we usually requires about 1.4 to 1.6. So the difference between this theoretical value of 1.23 and the actual value of 1.4 or 1.6, the difference is called as usually the over potential. So like as well as like these materials should have the proper band edge positions to split the H2 molecules, or let's say like to carry out the water splitting reactions. Additionally, because the number of incidence photons received per unit area in these semiconductors under Sanders condition is usually fixed. So to match these kinetics, the material should be catalytically active for either oxidation or the reduction reaction, or for both, and can be effective in transferring and transporting these photogenerated charge carriers among themselves. In addition, the candidates needs to be resistant. That means like it should be highly durable in the water electrolyzer, and should sustain or survive for long reaction in water under intense illumination. And of course, again at the last, these materials should fulfill all these requirements simultaneously. So when I say like these materials should fulfill these requirements, all requirements simultaneously, that means the materials with a suitable band gap, let's say about 1.6 to 1.7, or let's say around 2 electron volt, is like considered as an ideal material, but it will not be useful if it is not like a stable in the water electrolyzer. So like, for example, here I have mentioned about the oxides are stable, but problem with oxides are they are usually like very wide band gap semiconductors, whereas nitrides and sulfides semiconductors are usually a narrow band gap. Of course, not all, but most of them are narrow band gap semiconductors. But the problem with these nitride or sulfide semiconductors, again, also the phosphates, they are not stable in the electrolyte. So that means we still have a lot of scope in this research field to develop a nice materials, or let's not say ideal, to develop a nice material that can fulfill all these requirements simultaneously. That means efficiency, band gap, and the durability as well. So this is all about like a brief discussion about the different pathways for a green hydrogen production, and like how we can produce this green hydrogen using like different techniques, and then like a little bit about the PEC water splitting. That's because my most of works have been so far focused on the solar water spreading or the PEC water spreading using the different photoelectrodes materials. So I will now discuss our contribution to this green hydrogen production using the PEC water spreading with the different earth-abundant materials that we have developed in our lab. So keeping like the criteria in mind of about keeping the criteria of like high efficiency, suitable optical band gap, and the durability in mind, we have developed different materials. Of course, I'm not going to say that like we have developed these materials for the first time. What we have done is like we have choose those materials which have been like already developed by some researchers, and then we have like we have gave our input in either like improving their performance or improving their stability to produce the hydrogen using the scalable methods. So initially what we have done is like we have focused on like a widely explored TiO2 semiconductor photoanode, and then like we have tried to improve its performance by simply doping a sulfur into TiO2 lattices, and or by simply sensitizing a narrow band gap semiconductors, which is earth abundant compound like copper, zinc, tin, sulfur. Then we have also like focused on developing a different copper chalcogen and nanocrystals and their thin films using a fossil and green synthetic approaches for either as a photoanode or a photocathode, or simply for developing an unassisted water splitting system, which I will explain again in my last slides. lastly, you guys may be aware of the sluggish kinetics of a water oxidation reaction. That's because it requires a potential of about 1.23. So that's why people call it as call this reaction as a kinetically sluggish. So we, considering this in mind, we have also like focused our work on developing a different catalyst, mostly based on the iron, because the iron is earth abundant. And then loading these catalysts on different photoanodes, such as the iron oxide and the TiO2 again, to improve their performance as well as to improve their stability. So I will, in my next slides, I will explain about our results based on these different approaches that we have like utilized in our laboratory from last several years. So like we all know that the TiO2 has been widely investigated as a photoelectron in PEC water spreading after the first report of Professor Fujishima and Honda in 1972. So like you can imagine how much work has been done on the TiO2 itself as a photoelectron materials from like 1972. So why the people have been working on TiO2? Because it has many advantages over other materials. Mainly is like it's highly stable in aqueous electrolyte, and it's a completely non-corrosive. Second, it contains like earth abundant, cost-effective and environmental friendly elements. That is, TiO2 is composed of titanium and oxygen, which are like earth abundant, cost-effective and environmental friendly. Second, like next is like its energy levels are appropriate to initiate the water spreading reaction. However, still the efficiency of the efficiency for a PEC water spreading using this TiO2 is relatively very low compared to that of other materials that have been reported so far. So why? So like so there are several reasons why the efficiency of this TiO2 is relatively low compared to the other materials, like because of the different recombination that occurs in the TiO2. So how we can like improve the efficiency of the TiO2? So we can simply improve the efficiency of the TiO2 by simply passivating the surface states by formation of the catalytic heterostructures based on TiO2 with other semiconductors or noble metals. Like I have given, so you can see the examples such as the zinc oxide heterostructures with the TiO2, or metal such as the Ag heterostructures with the TiO2, or heterostructures of the rutile and anatized phases of the TiO2. Also, we can improve the performance by utilizing the visible light, because the TiO2 band gap, the band gap of TiO2 is like very wide. That means it cannot it can only absorb the light in the UV range. In the UV range. That means it is not able to like absorb the light in the visible region. So we can improve the performance of the TiO2 by again utilizing the visible light region, simply by doping your non-metals such as the nitrogen, sulfur, or the carbon, or by simply modifying chemically the with the transition metals or the noble metals. Also in cooperation of the plasmonic noble metals such as the platinum, IR, or silver, or gold, or simply sensitizing visible light absorbing nanocrystals, quantum dots, or nanoparticles such as the CDT, CDS, CDT, CDSE, and there are many more actually. But we are like actually focusing on developing earth abundant and non-toxic compounds, which we will see in next slides. So what we have done is like we have like, so of course this slide shows like these different approaches that I have explained in my earlier slides, we have like used to further improve the performance of these TiO2 nanorods that has been like fabricated using the hydrothermal synthesis method. And then we have simply like sensitized the nanoparticles of this copper, zinc, tin, sulfur. It's called as the CZTS compound, which has a band gap around like 1.5 electron volt, which is an ideal band gap to absorb the most of the visible light. So we have simply sensitized this CZTS on the TiO2 nanorod arrays. What else we have done is like we have also like doped the non-metals, that is sulfur, into TiO2 lattices to further reduce its band gap. That means to maximize its visible light absorption capability. And again, what we have done is like, so these two processes we have done individually, or let's say separately, and then we have combined these two all together to again maximize the effect of like a visible light absorption, or maximize the capability of harvesting visible light absorption from the CZTS nanoparticle as well as the sulfur doped TiO2 nanorod arrays. So let's see like our results based on these compounds. So like this is actually a schematic that represents like our approach, where you can see like we are mainly focusing on like improving the light absorption as well as the separation. So how this light absorption and the separation efficiencies can be improved using this like our approach. So usually the light absorption can be improved by simply doping sulfur into TiO2 lattices. So when we dope a sulfur, usually the band gap is reduced. I will explain why there is a reduction in the band gap after doping sulfur into the TiO2 lattices. As well as we can also improve the absorption of this TiO2 by simply sensitizing these visible light absorbing CZTS nanocrystals, which has a band gap of again 1.5 electron volt. But so like this is all about how we can like improve the absorption of these TiO2 nanorods. We can also improve the charge separation by again utilizing the like approach of sensitizing this TiO2 nanorods arrays. How we can improve the charge separation is that when we sensitize these CZTS nanocrystal arrays, there is actually a formation of type 2 heterostructures between TiO2 nanorods, or let's say between TiO2 and the CZTS, that usually like help us to improve the charge separation in CZTS nanocrystals or nanoparticles. And that's how like we design our research idea, and we carried out the further experiment in the lab, and we achieved the improved performance, which I will explain in my next slides. So before that, like I will briefly explain like how we prepare this TiO2 nanorods. So like we actually prepare a TiO2 nanorods arrays by simply using a well-established hydrothermal method by using by using simply a diawater hydrochloric acid and titanium butoxide and carrying out reaction at around 150 degrees centigrade for 9 hours, which was followed by annealing at around 450 degrees centigrade for 30 minutes. As explained earlier, the performance is comparatively lower. Then we again try to load the CZTS nanocrystals and also like doping of the sulfur into these TiO2 lattices. So these are the different like measurements results after like doping sulfur into TiO2 nanorods, and then like CZTS sensitization on TiO2 nanorods, and simultaneous CZTS incorporation into or sensitization onto sulfur doped TiO2 nanorods. So as can be seen from these like chopped and non-chopped LSVs, there is a like the CZTS sensitized sulfur doped TiO2 nanorods exhibited a significantly improved photocurrent density of about 8.84 milliampere per centimeter square, which is about 12 times higher than that of simply TiO2 nanorod arrays. Interestingly, this substantially enhanced photocurrent density in this CZTS and CZTS sensitized sulfur doped TiO2 nanorod arrays is almost equal to the sum of photocurrent density obtained from sulfur doped TiO2 nanorods arrays and CZTS sensitized TiO2 nanorods arrays, which clearly indicates that indicates the synergistic effect of the sulfur doping and the CZTS sensitization on these TiO2 nanorods arrays. As a result of these synergistic effects, we achieved the Hub cell efficiency, which is also called as applied bias photon conversion efficiency of about 3.14%, which is the highest among all the samples for this CZTS sensitized sulfur doped TiO2 nanorod arrays. The IPC of this, like, so we further measure the IPC to find out actual contribution of the sulfur doping as well as the CZTS sensitization on the TiO2 nanorod arrays. So as can be seen from the IPC that so after sensitizing the CZTS on the TiO2 nanorod arrays, there is a substantial photoactivity over a broad range. So this is the CZTS sensitized TiO2 nanorod arrays IPC spectrum. So you can see like there is actually a substantial photoactivity over a broad range from about, let's say, like 400 to about 700 nanometers. That suggests that after sensitizing the CZTS nanoparticles on the TiO2, there is an improvement in the visible light absorption. Sulfur doping, however, limited only up to 500 nanometer. That's because the reduction in the band gap is not that so high. And again, as a synergistic influence of like CZTS sensitization and the sulfur doping into TiO2 nanorod arrays, the IPC value greatly enhanced the photoactivity values, photoactivity over a broad range also significantly enhanced. We also measured like the S2 and O2 evaluation performance, which like shows the value of about 77 micromole after about 2 hours of water spreading reactions. However, if you see at the like a stability plot, you can clearly see that there is a 20% decrement in the photocurrent, in the initial photocurrent density value after like this CZTS sensitization on the sulfur dope TiO2 nanorods arrays. Again, the reason is because, as I explained in my previous slides, that the sulfur-based compounds are not stable in the aqueous electrolytes, and hence the reason is there is a slight decrement in the photocurrent density value, which needs a further research to again stabilize these compounds. So to shed a light in detail on the improved performance, we have like carried out the electronic bank structures calculation of the TiO2 and the sulfur doped TiO2. And like we find out some interesting like results. So the calculated density of states plots, that is DOS plots of the pure TiO2, yielded the band gap of about 3.07 electron volt, which is close to its theoretical value of about 3.1 electron volt. Whereas the calculated DOS of the sulfur doped TiO2 nanorods arrays reveal that the ES3P states are partially localized when the sulfur is, you can see from here, when the sulfur is incorporated in the TiO2 lattices. So what these like S3P states usually do? So actually these partially localized S3P states can contribute to the like a formation of the valence band, which leads to the shifting of valence band age upwards, resulting in a narrow band gap energy of about 2.2 electron volt, or let's say like of about 2.2 electron volt per sulfur doped TiO2 nanorods in comparison to 3.1 electron volt for like a pristine TiO2 nanorods. As I explained in my previous slide, that why there is a improvement in the PEC performance of these TiO2 nanorods after sulfur doping is that after sulfur doping there is a reduction in the band gap, or simply we can say there is a like upshift of the valence band age because of the sulfur doping. So like we also further carried out the like UV visible spectroscopy measurements, and then we realized that this like sulfur doped TiO2 nanorods arrays shows an additional shows a band gap value of about 2.7 electron volt. However, if you zoom the spectra and focus on the region of about 2.5 electron volt, or like let's say from about 2.2 electron volt to 2.5 electron volt, you can see an additional tail. And if you calculate the band gap from this additional tail, the band gap value comes about 2.28 electron volt, which further like confirm our observations from these DFT calculations. So what like I would like to like say here is that this double band gap behavior because of the sulfur doping is actually attributed to the gradient distribution of the sulfur doping concentration in our TiO2 lattices, and the reason why we have seen like two band gap tails in the sulfur doped TiO2 nanorods arrays. Now, to gain a further like insight into the electron hole transport mechanism, or let's say charge separation behavior in this CZTS sensitized sulfur doped TiO2 nanorods arrays and only CZTS sensitized TiO2 nanorods arrays, we have drawn these schematics which clearly explain this mechanism. So like we all know that like a suitable semiconductor heterojection with a type 2 band alignment is highly beneficial for efficient charge separation in a typically N-type photoelectrode, since it surpasses the electron-hole pair recombination and improves photo-generated or improves the transport of these photoexcited charge carriers. So when we incorporate the sulfur into TiO2 lattices, as I said, like from our DFT calculation, there is upshift of the valence band age of like from, let's say like, so like here is the TiO2 nanorods arrays without sulfur doping, and here is the TiO2 nanorods arrays with the sulfur doping. So if you see these two schematics, of course this is just only for a schematic purpose, you can see like there is upshift of this valence band age due to the sulfur doping that actually provides like a efficient channel or a pathway for this whole transfer from this TiO2 nanorods arrays to the CZTS nanocrystals or nanoparticles. Whereas in case of the TiO2 nanorods arrays, there is like a huge gap between the valence band edges of these TiO2 nanorods and the CZTS nanoparticle. So based on this, like we can simply say that this sulfur doping as well as this CZTS sensitization synergistically lower the charge recombination rate of these photogenerated electron hole pairs, and thus facilitate the participation of these more charged in the carriers in solar diamond oxidation, and significantly enhance the solar water splitting performance of these TiO2 nanorod arrays. So this is all about the TiO2, like improving the performance of these TiO2 nanorod arrays using the non-metal doping such as the sulfur and the narrow bandgap visible light absorbing compound sensitization. Of course, we can explore a difference like narrow bandgap semiconductors as a sensitizers on the TiO2 nanorod arrays, and you can still further improve the performance. But our focus was on using the CZTS. That's because that's our like expertise. So like as I said, that's our expertise. So our next work was focused on like again developing this copper chalcogenide nanocrystals using like a relatively simple and the facile green synthetic approach. Before that, I would like to just tell you that like usually the techniques such as the hot injection or the heat up approaches that are used to produce these kind of nanocrystal like monodispersed nanocrystals, they usually like contains very highly toxic and the flammable solvent such as oleamine, octadecene, and oleic acid, etc., which are the organic solvents. So to avoid that, to avoid use of the highly toxic solvents, we have like come up with an idea of using vegetable oil and deputatic solvents as a reaction media to synthesize these copper chalcogenide compounds like such as the CZTS and the copper antimony sulfides, which I will discuss in my next slides. So we use the like vegetable oils to produce the CZTS nanocrystals of sizes about around like 15 to 20 nanometers, and these nanocrystals are synthesized at different reaction temperatures. And you can see like with increasing reaction temperature, there is an increase in the size of the nanocrystals. Of course, I will not go in detail again. Then we carried out different like characterizations to further confirm the phase formation, and then we found out that at all reaction temperatures, there is a formation of the CZTS nanocrystals. So the CZTS nanocrystal that we synthesized, we again sensitize these CZTS nanocrystals just like in our previous approach. But this time, like we sensitized these CZTS nanocrystals on TiO2 nanorod arrays, which was passivated with the zinc oxysulfide layers. So just to let you know that we passivated the surface of these TiO2 nanorod arrays using atomic layer zinc oxysulfide. The reason because the TiO2 surface, the TiO2 has a surface defects, and the passivation of those surface defects using zinc oxysulfides usually improves the performance of these TiO2 nanorod arrays. And then again, like we loaded these like or decorated CZTS nanocrystals on this one, and we observed the improved performance until up to about 15 milliampere per centimeter square. Of course, there is no need to explain in detail, but like I just want to tell you that so the performance of these TiO2 nanorod arrays can be significantly improved by simply doping a non-metal such as this like sulfur, or again doping of this like visible light absorbing compounds such as CZTS or copper antimony sulfides, or CDS or CDSC. Then again, what we have done is like we again like try to develop an approach using a eutectic oil as a reaction media to synthesize these different phases of copper antimony sulfide. These are the again copper chalcogenide compounds, which has a suitable band gap of about like around 1.3 to about 1.7 electron volt. So what is this like a deep eutectic solvent? So we use the ethylene as a deep eutectic solvent, which has a low viscosity, and the reason we use we moved our synthetic approach from vegetable oil to this low viscosity deep eutectic solvent is that in our like previous experiments, we observed that there is a problem with the washing of the nanocrystals because of the high viscosity of the vegetable oils. You may also observe it in your kitchen. Like if you heat the oil, our cooking oil, let's say vegetable oil, to about 300 degrees centigrade, or let's say like about 250 degrees centigrade, they are become more and more viscous. And that's what we observed in our experimental things as well. And when the solvents become more and more viscous, then we usually get a difficulty in washing those like nanocrystals prepared using those like solvents, let's say vegetable oil in our case. So the reason like we moved it to the deep eutectic solvent because its viscosity is too low, and which usually like help us to wash those solvents, wash those nanocrystal quite easy. And again, like this diptychic solvent is non-toxic. So using this diptychic solvent, like we synthesize these 4 different phases of like copper antimony sulfide nanocrystals, which has a band gap from about, of course, these are the theoretically predicted, and the which ranges from about 0.94 to about 1.75 electron hole. That again suggests that these are good compounds to harvest the maximum visible light absorption. So these are the simply characterizations like XRD and the TM. From TM, you can see that like the nanocrystal sizes ranges from about 8 nanometer to about like 22 to 25 nanometers. So in this case, what we have done is like we made a thin films from a nanocrystals of this from nanocrystal ink of these nanocrystals, and then like we prepared a thin films, and we use these thin films as a photocathode instead of photoanode for water spreading reactions. So if you see like these 2 plots, you will clearly see that. So this like a bare copper antimony sulfide. So these are the 2 different phases which has a different band gaps, and the reason like we tested both of them because of their different band gaps, and we wanted to like find out which compound like performs well, and then correlate their performance with their band gap energies. So you can see like both bare like Cu3sbs4 and the CuSbs2 shows the negligible photocurrent density towards the water splitting reaction. That means these compounds are not able to perform the water splitting reactions very well. But with the addition of the platinum catalyst on these both photocathodes, you can see there is a slight improvement in the photocurrent density. Again, the performance improvement is not that drastic. So what we did is like we incorporate the N-type CDS layer in between this platinum and this absorber materials to form the PN junction. And the intention to form this PN junction is to improve the charge separation by utilizing the benefits from this PN junction heterostructures. And we saw a drastically improved photocurrent density of about 1.28 milliampere per centimeter square for Cu3sbs4 CDS platinum, and about 2.72 milliampere per centimeter square for copper antimony sulfide, that is CuSbs2 CDS and platinum. So you will you can see the performance improvement in these samples are a little bit higher than this one. Again, we can correlate that to the band gap energy of about 1.62 electron hole, which is like quite optimum to harvest the maximum sunlight, whereas this compound has a band gap energy of about 0.94 electron hole. That again explain why the performance in these 2 is slightly different. We again tested these samples for their durability test, and we again observed, just like in our previous experiment, that the samples are not so stable in the aqueous electrolyte, and there is a decrement in the performance after stability test of 2 hours. And reason again, the sulfide compounds are usually like corrodes in the aqueous electrolytes, and again we need a further work to stabilize these compounds in aqueous electrolyte. So after like careful analysis of these compounds, what we have done is we employed the UV like ultraviolet photoelectron spectroscopy to find out the band alignment of this Cu3sbs4 and the CuSbs2 material, and then like we designed an unassisted system. Of course, what we have found out that using this ultraviolet photoelectron spectroscopy studies that the copper antimony like Cu3sbs4 material is a good sensitizer to load on the NiO nanosheets, which will act as a photocathode, whereas CuSbs2 is a suitable sensitizer for TiO2 photoanodes, for a TiO2 nanorods, which will act as a photoanode. So like in short, like we studied the band alignment, and we then fabricated the photoanode and photocathodes based on these sensitized quantum dots, and we assembled the unassisted water spreading system. When I say unassisted water spreading system, is that you don't need to provide an external potential to drive the water spreading reactions, because these 2 electrodes are capable enough to produce the water, to produce the hydrogen by simply absorbing the sunlight. That's because we are using the semiconductor materials on the both side as a photocathode and as a photoanode. So these are simply like LSV measurements from where you can like understand like there's an improvement in the photocurrent density after sensitization of this copper chalcogenide compounds or like a nanoparticles on the NiO and the TiO2. Not going to explain about the value improvements. That's because it can simply like seen from this like plots. Of course, we'll explain a little bit about the IPC. So from IPC, you can see that like after sensitizing these copper chalcogenide compounds, like let's say copper antimony sulfide, Cu3sbs4 and the copper CuSbs2 on NiO and TiO2, you can see like there is an improvement in the visible light activity of this NiO and visible light activity improvement of the TiO2. That simply suggests that these compounds act as a visible light absorbing compounds to improve the like visible light absorption capability of the NiO and the TiO2. So like we again like as I said, like we studied the band element and then we like fabricated this like a photoanode photocathode to actually produce to actually develop unassisted photo like water spreading system. So this slide shows all about the like a measurement of this unassisted system, that is a two photoelectrode system. So you can see like we initially measured this H2 and O2 evolution rate, which was found to be like about 1.52 micromole and O2 of about 5.8 micromole. Of course, there is a little bit discrepancies or differences in the values because we measured the like H2 separately for a photocathode and we measured the O2 separately for a photoanode. Then we fabricated this Z-clim system and then we realized, so you can see like this is actually a crossover in the LSV curves, which was obtained by simply overlapping the LSV curves of this photoanode and the LSV curve of photocathode. And you can see even at a zero potential, we can achieve a photocurrent density of around 1 milliampere. It should be, it's about like 0.97 milliampere per centimeter square. What that exactly means? That means without even applying a potential, we can achieve a photocurrent density of about 0.97 milliampere, let's say about 1 milliampere per centimeter square. That means we don't need an external like a bias to carry out or to initiate this water splitting reaction. And hence we call it as an unassisted water splitting system. So by simply like analyzing this crossover of the LSV curves separately from the photoanode and the photocathode, we fabricated the two electrode system and then we measured the performance and we achieved the photocurrent density of about 0.84 milliampere per centimeter square, which is close to about 1 milliampere per centimeter square. However, slight decrement can be attributed to the resistance that arises from the connections problem. Finally, again, like we tested the stability and then we observed a kind of similar trend that there is a decrement in the current density values after like 1 hour of the stability test. That again can be correlated to the like ability not to sustain harsh conditions of the aqueous electrolytes during the light illuminations. So far, like I have explained you all about like improving the performance of the TiO2 by simply like a sulfur doping or copper chalcogenide nanocrystal sensitization. And then like each time like we have observed that like there is a decrement in the photocurrent density value after a stability test of about 1 hour or 2 hours. And then we realized like every time we use the like a sulfide based compounds or chalcogenides, we have been like observing the decrement in the like a photocurrent density values. So we came up with an idea to stabilize this like a photocathodes or photoanodes. Of course, we mainly work on the photoanodes. We have also worked on the photocathodes, but I have not included those results in here. So like, what is that approach that we employ? So like one way like to further like improve the stability is like we can load the AP based catalyst or any catalyst on this like photoanodes to improve the water oxidation kinetics as well as the stability. I will quickly like explain these results because I think I'm running out of time. So we developed this like electrolysis deposition approach to prepare this AP based catalyst, which is like a kind of like first method or a first approach which avoids the use of excessive reaction temperature, just like in hydrothermal method, or which does not require the external bias, just like in electrodeposition methods, which are commonly used methods to prepare the catalyst for like water splitting reactions. So we prepared this like iron oxide catalyst and then we incorporated the Mn And then we find out like after incorporation of the Mn into this catalyst, there is an improvement in the like ore potential values to about 246 millivolt. So after loading this like a catalyst on this photoanode, that is Fe2O3, because we just wanted to like create a photoanode system that comprises all earth abundant metals, that is Fe. So we choose the Fe2O3 again because of its suitable band gap as well. So there is an improvement in the photocurrent density value to about 3.36 milliampere per centimeter square, which is kind of a significant improvement after this catalyst loading. And if you see the stability plot, you will understand that even after like a stability test of about several hours, the photocurrent density value of this photoanode is almost kind of like a similar, and that suggests the role of this catalyst in stabilizing the photoanode materials as well as improving their performance. In like in our next work, what we have done is like we have also find out the possibility of the or the role of this Ni doping into the iron oxide hydroxide, as well as the different like catalyst support, which is like nitrogen doped graphite foam. So with a similar like kind of approaches, we observe that with a nickel doping, there is a significant improvement in the ore potential value. That means ore potential value is drastically reduced thanks to the nickel doping, which actually modulates the electronic structure of the iron oxide hydroxide. And this highly conducting nickel nitrogen doped graphite foam also helps to improve the electrical conductivity. And that again, all like improves the performance. So based on this like initial like electrochemical measurements, like we load this nickel based iron oxide hydroxide catalyst on these TiO2 nanorods arrays. So these are the basic like characterizations. Like a SEM, you can see like there is a formation of the core cell that is nanosheet and nanorod heterostructures, which was again confirmed using this like elemental mapping. So you can see like there is a like a very thin, ultra thin layer of these nanosheets of the NiPOH on the TiO2 nanorod arrays, which has covered all TiO2 nanorod arrays. So photoelectrochemical measurement again showed that there is a potential shift as well, and there is an improvement in the photocurrent density value. But interestingly, in this case, like we have also observed that this NiPOH also contributes to the like improvement in the visible light absorption capability of this TiO2 nanorods arrays, because the NiPOH like shows the band gap of about like around 2.3 electron hole, and that's what like we have observed from this IPC. These are the basic EIS and the like lifetime analysis, which I'm not going to explain. But yeah, notably, if you see the like stability plot, we carried out the stability test for 24 hours after like decorating this NiPOH catalyst on the TiO2 nanorod arrays, and you can see that there is not even like a 5 to 10% decrement in the photocurrent density value, which suggests that how effective these catalyst materials are in stabilizing these compounds or photocathodes or photoanodes, as well as improving their performance. So this is the final summary. So I will conclude my talk by simply giving a final summary. So what we have done is like we have like achieved the improvement of these TiO2 nanorod arrays, that is performance improvement, by simply doping the metals or non-metals and the visible light absorption absorbing nanoparticles, as well as the catalyst loading. And then we have also like showed different. We have also like designed an unassisted water spreading system based on these copper chalcochrome and nanocrystals, which has a tunable band gaps. And finally, like we have demonstrated our scalable room temperature deposition method to prepare this metal oxide hydroxides catalyst, and again to load this catalyst on like a photocathodes or photoanode to improve their stability drastically. So these are some of our artworks which has been like featured or which has been published by RAC and the ACS journal that demonstrate the impact of our work. And finally, I would like to like thank to my mentors, specifically like Professor Xiaojing Hao, Science Chair Professor Martin Green, who is a pioneer like in a silicon solar cell, and Science Chair Professor Rosamal, who is a world leader in the photocatalysis. And not but lastly, I would also like to thank like ARC, that is Australian Government, Australian Research Council, and European Commission for awarding me with the Early Career Researchers Award. Thank you.
Thank you very much, Dr. Suryavanshi, for such a wonderful talk, which was in a simple and lucid language. It was very much informative. We too are working in photoelectrocatalysis, but for other purpose. But what I thought, you have covered this topic from root, and you have presented your result, and you have explained to the audience what actually you are working or what actually you are doing so far as hydrogen production field is concerned. So let me summarize what you have. Of course, you have given summary of your lecture, but what I have taken down on, and as a part of chairman, I should summarize what you have explained. So
Sure,
you have rightly explained the concepts about the global warming, the cause of global warming, and you told what are the way outs of decreasing the global warming, and the ultimate strategy is to use the renewable energy, and that to solar energy. And we know solar energy can be used for different purposes. And you have explained in your lecture how solar energy can be used for the production of hydrogen and how it can be used for water splitting. We know water is a very simple molecule of 3 atoms, 2H and 1O, but it is very difficult to break the bonds of O and H. And from your lecture, we could understand that how solar energy can be used for the production of H2 and O2 by applying a bias and by applying the solar energy. We know to split the water, 237 kilojoule energy, particularly 1.23 volt or correspondingly 57 kilocalorie energy is required to give to the water through electrodes. So the role of electrodes is very important. It could be photoanode or photocathode. You explained in your lecture how the different strategies can be used for development of photoanode and photocathode, and how both the photoanode and photocathode, which are semiconductor in particular, can be useful for improving the ore potential and improving the photocatalytic efficiency. I could know the ideas of blue and gray and green hydrogen from your lecture, and how the hydrogen storage can be used and how it can be produced via green route like biomass and other technique. But you explained in detail the idea of PC water splitting, where the reduction and oxidation reduction, utilization of electron and hole pair, which is produced in the photoelectrochemical process when we illuminate a semiconductor electrolyte junction by a solar light or electromagnetic radiation of appropriate energy. The electron and hole pair is generated, and how this can be utilized. So the efficiency of the photocatalytic reaction depends on how you are instrumental in separating the electron and hole pair, how you improve the quantum efficiency of your device. So the various strategies and the materials like very highly chemically stable TiO2, which is extensively used for photoelectrochemical water splitting, and iron oxide, the heterostructure of zinc oxide, titanium oxide, and sensitization, the chalcogenide like copper, antimony sulfide chalcogenide can be used. And you explained how we can harness most part of the electromagnetic spectrum, particularly visible part, for the purpose. And you explained the different approaches like use of nanorods and sensitization of the solar cell. And these materials, nanorods and other materials, they are prepared in your laboratory by a cost-effective chemical technique. That is a very important thing, because with the help of physical methods, it is very easy to prepare a material, and high quality material can be used, but these are costly methods. But you explained how chemical methods, which are relatively simple and which we can adopt in our laboratory, in your college also we can do this. So overall, the concept of water splitting and what is happening in this field, and as far as your lab is concerned, you have explained in a great manner. So I'm pretty impressed by your way of lecturing. Here are few of questions which I have asked by the audience. Which water is good source for hydrogen, if marine or fresh water? There are two options, is the question. Mahesh.
Thank you, sir. Thank you. Of course, like that's a really good question. So like for now, there are a lot of difficulties using a marine water for a water spreading because like they contain a lot of different alkali metals, like alkali elements. Of course, we have been working on like using marine waters. That's, let's say, seawater. But we didn't get a lot of success in using the marine water. So let's say for now, fresh water is a kind of like a base source for now to produce the water using to produce the hydrogen using the water.
Can we use plants for production of hydrogen in PC catalytic reaction? This is one of the questions. Can we replace plants by artificial photosynthesis, etc.? So can you focus some light on this aspect?
So like, sorry, sir, actually, I didn't get the question. What kind of plants you mean?
No, you see, people use green root for synthesis of nanomaterials, like they use plant extracts for preparation of nanomaterials. So similarly, such aspects or such strategies of using green root, can we use for production of hydrogen or water splitting? That is the question, I think. HP, who is HP? I don't know. The name is missing.
So may I talk in between? Hello?
Yeah, go ahead.
Yes. It's myself, Smita Zugde from Botany. I'm asking.
Madam, you are speaking.
Yes.
HP, I did not get your name, therefore. Yeah. Anyway, hope I have correctly asked the question.
Yes, actually, Dr. Mahesh sir said that it is like artificial photosynthesis in first, second, or third slide. In fact, the water splitting of the water is the first important chemical reaction in the photosynthesis in plants. It is half of the photosynthesis. So till now we haven't prepared food artificially in absence of the plants, because that chemical reaction we have not produced in the laboratory itself. But whatever presentation today happened, it is like a splitting of the water. Entire energetics has been expressed by Dr. Mahesh. So is it possible such chemicals we can use, means such anodes, cathodes, such cell we can incorporate nearby leaf of the plant to enhance photosynthesis? Because what plant needs is, after all, just sunlight to split the water molecule for the photosynthesis.
Mahesh.
Yeah, I think, sir, yeah, probably, of course, I'm not so like so sure about like the answer of this question, because we never thought of like using like a plants to again improve the efficiency.
But that would be a good topic.
Yeah. Yes, definitely. So like our focus is like mainly developing materials like semiconductor materials. So our major focus is kind of like material science, not a plant or kind of biology. Of course, that can be a possibility, but I would rather not to like comment on this question for now.
Okay. Thank you, Mahesh. Some other questions? Anybody? This session is open for discussion already.
Dr. Mahesh.
Dr. Killedar, Professor Killedar wants to ask the question. You can directly ask the question.
Yeah, sir. What do you say about how much energy we are putting in electrolysis and how much energy we are getting after production of hydrogen? Whether this process is useful really?
Yeah, so like, yeah, as I said in my, as I have shown you in different slides. So for now, like solar water splitting, that is like a direct water splitting, or simply say photoelectrochemical water splitting, which is not so efficient at the moment. The highest efficiency for like photoelectrochemical water splitting so far is about 20%. That means like if you shine a light, then we can take only 20% of like hydrogen production from that cell. But again, like when I say 20% efficiency for like photoelectrochemical cell, the semiconductor materials that have been used to achieve this 20%, they are very, very expensive. Like they are from like 3,5U group compound. So like it's a gallium arsenide or gallium nitride. So like, of course, like, so again, like the techno-economic analysis, as I said, suggests that the direct water splitting can be a future, like it can be a future like technology to use to produce the hydrogen using sunlight and water, if we achieve the stability over like several hours, let's say like about 100 hours with efficiency of about even 5%. So like if we use the low cost materials And then if we achieve the efficiency about 5% and the stability over 100 hours, then probably that can be possible. But as I said, for now, I think these processes are not so highly efficient. And again, like just to add on it, so the technique which is like a PV assisted water splitting, like we use the like a sunlight or we use the electricity which is generated from the PV, like photovoltaics, and then we give that to the electrolyzer, which is kind of like technological readiness level. So this technique is already like near about the commercialization. So that is possible at the moment, and which has a efficiency of about 65 to 70%. So I would rather say like that approach of PV electrolysis is much more efficient than the PEC water spreading. But again, both approaches has their perks and like benefits and that like advantages and disadvantages.
Okay. So this photoelectrolysis or this concept where we use semiconductor and solar cell or solar energy, there is a big loophole where we cannot use whole all electron hole pairs for our purpose, right? This is that is the reason why the quantum efficiency of your system is low. So his question, I think, Professor, ask you how to improve the quantum efficiency. What are various strategies to improve the quantum efficiency? So you answered the question. Some other questions? Somebody else?
Now can we conclude? We have to start the next session.
Yeah. So I would like to ask a couple of questions, Mahesh.
Yes, sir. Sure.
There are various strategies to improve the quantum efficiency or the yield of your process of water hydrogen production. Is it not?
Yes.
So if we to increase efficiency, is the idea of increasing the photo potential or photo voltage and photo current? So photo voltage and photo current, they can be improved in different approaches, right? So if we simultaneously improve photo voltage and photo current, that would be one of the approaches to increase the. You please comment on this.
Yeah, sir. Like as I shown, like in my slides, like we have used the different approaches, right? Like let's say like kind of sulfur doping to improve the visible light absorption. That usually improves the current density, not the potential. But if you dope or like not the dope, if we sensitize the visible light absorption like nanoparticles, for example, let's say CDS or the CZTS, then there might be there is a possibility to improve the current density as well as the potential as well. Third approach is like a catalyst. So here the catalyst plays a major role in improving the current density as well as the potential. Again, it not only depends on these three different strategies, it also depends on the semiconductor materials itself. So if you see the recent like a recent sensation of the halide perovskite material, so they are actually a defect tolerant materials. So when I say a defect tolerant, that means these compounds have a minimal amount of defects. That means the possibility or the efficiency of these compounds are very, very high. But again, there is a problem with these compounds. So like one compound is nice when it comes to the like efficiency improvement, but at the same time that compound is not stable in the water. Other is stable in the water, but that compound's efficiency is not so great. So like what I suggest is like probably including all different strategies all together. So let's say like let's take a halide perovskite, which usually gives the potential of about 1 volt or open circuit voltage of about 1 volt and the current density almost about 25 milliampere per centimeter square. So if we take that particular compound and if we like try to improve its stability just for about like, let's say even like 100 hours, then we might be able to achieve the final goal of this like a PEC water splitting system, which has been predicted by techno-economic analysis. So let's say like we can achieve simply. So already people have worked with these halide perovskite compounds, which have like shown the efficiency about 10%, but the stability is only for like couple of hours, even not like 1 hour or 2 hours. So final, like in short, like we have to choose the compounds which are a defect tolerance. That means they should be high quality and they should be very highly efficient. And then we should protect those like semiconductor compounds with a catalyst. Those can also again like accelerate the water oxidation or reduction reactions and further improve the efficiency.
Okay, this discussion cannot be never ending. It would be it will be continuous. So go on and on. Because there are another questions. Madam has asked again how to calculate the efficiency of photolysis. Of course, Mahesh can answer these questions when you contact him personally. Now, as Professor Killedar has already mentioned, we need to go to another session and there is another lecture. I think this is the time to conclude this session. I take this opportunity to thank Dr. Mahesh Suryavanshi, our alumni, to spare his time and give such a wonderful talk in this international conference. I am also thankful to organizers to give me this opportunity to chair this session. So thank you all, and I hand over the session to the anchor.
Thank you so much, sir.
Thank you very much, Professor Rajpure sir, and thank you very much, Dr. Mahesh Suryavanshi sir. Your session was very interesting and very knowledgeable. Now, to deliver the vote of thanks, I invite Professor Dr. Killedar sir, the Vice Principal of Shahu College.
So I am very much thankful to Dr. Mahesh Suryavanshi for delivering a nice information talk on topic pathways of green hydrogen production. Thank you, sir, for accepting our invitation and sparing your valuable time with us. I am also grateful to Professor Dr. K.Y. Rajpure, Head Department of Physics, Shivaji University, Kolhapur, for accepting our invitation and sharing this section. I also extend my thanks to the student and teacher participants for attending this session in online mode. I am also thankful to Ms. Prachi for anchoring the session. Thank you. Now this session is over. Now we are going to conduct the next session, that is from statistics.
Thank you, sir. Now to introduce our next chairperson, I invite Mr. P.S. Chaugle sir, the Assistant Professor from Department of Statistics.
Good afternoon to one and all. I, Mr. Prakash Chaugle, Head Department of Statistics, present here to welcome Research Person Dr. D.M. Saktis, sir, and Chairperson Professor Killedar, student, teacher, participant. Let me introduce Professor Killedar, Chairperson of this session. Professor Killedar is working as Vice Principal and Head Department of Physics. He is teaching physics since last 35 years. He has shouldered the administrative and other responsibilities such as in charge principal of Rajarshi Chhatrapati Shahu College, Kolhapur, in charge science faculty of RC Shahu College, Kolhapur, Head Department of Physics, BOS member of Shivaji University, Kolhapur, Chairman and member of LIC Committee of Shivaji University, member of editorial board of Vignan Patrika, regional chairman of Rayat Vignan Parishad of Rayat Signal Satara. He worked as coordinator, convener of national and international conference and workshop. He awarded by following awards. He stood the second in PhD for third science faculty vice chair Satara. He stood fifth in Shivaji University merit MSc list. Best teacher award in 2014 given by Vatsala Foundation, Kolhapur. He worked as MPhil and PhD guide of Shivaji University, Kolhapur. He, under his able guidance, one student completed his research work. He completed 3 research project, minor and major project, under out of 2 sanctioned by UGC and 1 sanctioned by Shivaji University, Kolhapur. He has published more than 40 research papers in national and international journals and proceedings. He has attended and presented the research paper more than 19 international and national conferences and workshops. He has published 1 reference book and 5 textbooks in physics. He has delivered more than 45 guest lectures as a research person. When I welcome the research person and chairperson, I request to Professor Killedar sir to conduct this session.
Okay, thank you, sir. Thank you, sir. It is my pleasure to introduce today's resource person, Dr. Deepak Sakte sir. He is presently working as Associate Professor, Department of Statistics and Applied Mathematics, Central University of Tamil Nadu. Dr. Sakte sir has completed his PhD, MSc and BSc education from Shivaji University, Kolhapur. He has also qualified SET examination in year 2008. He is a postdoctoral fellow, Department of Biostatistics and Epidemiology, Augusta University, Augusta, USA. He has a teaching experience of 12 years at PG in Statistics and PG Diploma in Actuarial Science. He has shouldered administrative responsibilities as head of the Department of Statistics and Applied Mathematics, Central University of Tamil Nadu, coordinator for postgraduate diploma in Actuarial Science, Shivaji University, Kolhapur, coordinator for MPhil PhD Statistics course, Shivaji University, Kolhapur. He has also worked as a task force committee member, International Affairs Cell, Shivaji University, Kolhapur. Dr. Sakte has contributed his subject knowledge in Board of Studies and worked as Chairman, BOS, Department of Statistics and Applied Mathematics, Central University, Tamil Nadu, member, BOS in Statistics, Dhanajrao Gadgir College of Commerce, Satara, member, BOS Statistics, Sadhguru Gadge Maharaj College, Karad. Now, under his able guidance, 3 students are working for their PhD. He has published more than 15 research papers in national and international level journal. He has presented more than 14 research papers in conference, seminar, and symposia. He has completed 1 minor research project sanctioned by DST SERB. The amount mobilized is about 17 lakhs. He worked as a referee for statistics in medicine, SAR and QSAR in environmental research, Journal of Applied Statistics, Communication in Statistics, Theory and Methods, Model Assisted Statistics and Applications, Current World Environment. He has a membership of academic bodies such as Life Member International Indian Statistical Association, Life Member Indian Society for Probability and Statistics, Life Member Shivaji University Teachers Association. He has delivered more than 32 invited talks in various conference, symposia, and FDP. He has worked as a convener, member of organizing committee for more than 12 national and international level seminars and conferences. Presently, he is working as head of the Statistics and Applied Mathematics, Central University of Tamil Nadu, India. So with this brief introduction of Dr. Sakte, I request Dr. Sakte sir to enlighten our audience with his talk on topic non-parametric tests based on ranked set sampling. Once again, I welcome today's resource person, Deepak Sakte, the student and teacher participants to this session. I hand over to Sakte sir.
Thank you very much, sir. Am I audible?
Yeah, okay, proceed.
Okay. Yeah. Thank you very much. A very good afternoon to all of you. At the outset, let me thank the organizers of this conference and the chairman of this session, Dr. Killedar, for giving a nice introduction. And of course, let me thank the organizers of this conference, particularly Principal Major Dr. R.S. Dubal, and the convener of this conference, and even Dr. Tejasvi Kurne, Professor P.C. Chougule, and others for giving me an opportunity to be a part of this session and deliver a talk on area of my interest, which is concerned with non-parametric procedures. for based on rank set sampling. Let me share the screen. Is my screen visible?
Yes, sir.
Is my screen visible?
Yes, sir, it is visible.
Okay. So friends, today I'll be talking about non-parametric tests based on rank set sampling. Before actually moving on to the actual topic of a non-parametric test, I shall first give a brief introduction about rank set sampling, and then I'll move on to non-parametric tests. So the outline of my talk would be rank set sampling, then two sample location problem. Then I'll introduce one of the proposed tests, which is a joint work with one of my PhD student, and then I'll throw some light on the performance evaluation of the proposed test through simulation study, and then I'll illustrate the proposed method using a real data. Let me be frank, like I know this is a conference for advances in science and technology, and most of the audience may not be from the field of statistics, and the deliberations in this session from my side would be a little bit hardcore statistics. I'll try to make it as simple as possible so that whatever the message I want to deliver, that will be reaching to each and every one of you. So if at all there are some notations in my slides, kindly bear with me, because without which I cannot proceed. So you can just ignore the notations and the equations which I'm showing and focus more on what I'm talking about and the essence of the equations and whatever it is. So basically this rank set sampling, which we are going to discuss in this session, this is an alternative sampling procedure uh, for the usual sampling procedures which are used in real life. Nowadays, you might have heard, like, whenever something has to be estimated based on data, simple random sampling is the first choice which a researcher from social sciences or even from general sciences look into. But because of the non-representativeness of the simple random sampling for the complete population, and sometimes the results which are to be achieved at a greater precision based on a smaller sample size, that may not happen based on a simple random sampling. Of course, there are some advanced alternatives for simple random sampling, like stratified sampling or systematic sampling or double sampling and so on. But this rank set sampling provides a much superior way of estimating the unknown entities for the population based on a sample more effectively as compared to the simple random sampling. So my entire talk would be based on this rank set sampling. I shall first introduce what it is, when it was actually introduced into the literature of statistics, and then we'll move on to the actual procedures. So McIntyre is actually considered to be the father of rank set sampling, and he introduced this concept for the first time in 1952. For many scientists, this would be to be considered as a recent introduction in the field of statistics, because statistics field was actually developed not more back in the past, but it is a kind of a very recent development. So 1952 is not very far behind, but still, because of its complicatedness and computational aspects, it was not that much popular when it was introduced by McIntyre for estimating certain entities in the field of agriculture. The major reason for not being more popular was the lack of computing facility. But now, with the rise of computers and a highly computational environment which is available in each and every part of the academics, we can definitely think of rank set sampling as a best alternative for a simple random sampling. So McIntyre essentially introduced this rank set sampling for the first time in the context of obtaining reliable farm yield estimates based on sampling of pastures and crop plots. This is usually needed because in practice, when we if you have seen the estimates produced by the government of India for specific crops like yield of wheat, yield of rice, yield of meaning whatever the food crops which we are usually having are being cultivated in India. Their estimated yield is always given at the end of year based on which GDP and all, meaning their contribution to the GDP is also computed. So you might have seen like agriculture is the highest contributor to the gross domestic product of India. So computing the accurate yields of these crops matters a lot, and how it can be done. If we try to compute it by doing a census survey, definitely it is not possible because census has its own drawbacks. And if you go for a sample survey, then whether simple random sampling would be helpful or some other sampling procedures are more better. And you can see, like, as McIntyre introduced it for this particular purpose, the importance of rank set sampling essentially is visible from this example itself. So this I shall of course throw more light on like what exactly it is and how it is different from SRS. But before that, let me talk about some developments in the theoretical aspect of rank set sampling. So in 1968, this Takahashi and Wakimoto, and of course in 1970, Takahashi developed a methodology for rank set sampling. When I say methodology, I essentially mean estimating population mean and estimating the variance of the population mean, where the key aspects which were handled in these two publications. One was by Takahashi and Wakimoto, and the other one by merely Takahashi. So they gave the foundational theory for rank set sampling, like estimation of mean and its variance. Later on, when the inferential aspect was to be touched upon in 1988, you can see the difference. In 1952, the method was proposed, and the inferential aspect was actually handled by Stokes and Sager in 1988. There is a long gap, and this was another issue. Like, nobody bothered to develop the foundational aspects of this procedure. But in 1988, Stokes and Sager gave an estimate of population distribution function based on rank set sample, which is much superior than the its counterpart obtained from simple random sample. So that was the ignition point, I will say, from which the research in rank set sampling began at a velocity, and now it has picked up. And now you can see almost every procedure which is based on rank set, which is based on simple random sampling, is being thought of for rank set sampling because of its efficiency. So let us see, like, in what ways or in what examples this rank set sampling can be used, or how people use it essentially. In 1980, Martin and his co-workers, they actually wanted to evaluate or rather estimate shrub phytomass in Appalachian oak forest. And in doing that, basically what is involved is counting the number of each vegetation type in randomly selected blocks of forest stands, which is essentially time consuming. But on the other hand, ranking of a small number of blocks by visual inspection can be done quite easily. This is the crux. Like, if we can do something, if we can enumerate something which is highly correlated with the variable of interest, then we can think of rank set sampling and use that auxiliary information to estimate the variable of interest and parameters associated with it. So the second example which I would like to share is from Samvi 1999, and this is actually concerned with the bilirubin level in blood for newborn babies. This is a common experience, like whoever has kids or whoever has seen kids born in their family, usually there will be a symptom which is actually concerned with hepatitis, and the pediatrician who is looking after that kid will definitely tell that not hepatitis, I will say, but jaundice particularly. So the pediatrician will tell that the kid is suffering from jaundice and he needs light treatment. So why that jaundice is there? Of course, we are not going to get into the details why jaundice is there, but how one can identify whether jaundice is present or not. Basically, when a kid is suffering from jaundice, the bilirubin level in blood will go high. Bilirubin is a chemical which is released by liver, and since jaundice is a liver disease, this bilirubin level will go high in blood whenever jaundice occurs. When this bilirubin level is actually an indicator of the presence of jaundice, and further, because of high levels of bilirubin in blood, what will happen is like the color of the peripheral parts of the body, particularly you can talk about skin becomes yellow, and that yellowness is more visible on face, chest, and lower parts of the body. And at the same time, the yellowness will actually move from the central part of the body towards the terminal parts, and whole body becomes yellowish. So the strength of the color and the levels of bilirubin, they are highly correlated. And whenever it comes to like testing for bilirubin, whether how much it is increased and how much not, what has to be done is like a sample has to be taken from the baby, and based on which a test has to be done, a blood test has to be done for checking the bilirubin level. So when a sample is to be taken, the kid has to be punctured. I mean, his vein has to be punctured, and then some blood has to be drawn. That is painful, and since it is a newborn baby, you can imagine how much trouble it will give to the newborn babies. So sampling from every newborn baby would be difficult. So what can be done? If we need to have an accurate estimate of bilirubin level when jaundice is present, then in that case we need to sample more. So can we sample less with some proper mechanism without losing efficiency, or rather gaining more efficiency on the usual simple random sampling? Then that would be definitely beneficial and less troublesome to the newborn babies. An alternative is rank set sampling. So the reason for going for rank set sampling is the last line on the slide. Since as the yellowish color goes from face to the terminal parts of the whole body, the level of bilirubin in blood goes higher. So they are highly positively correlated. So can use this yellowishness of the body, which can be seen visibly, based on which we can categorize the kids like they are having high level of bilirubin, moderate level of bilirubin, low level of bilirubin, and accordingly we can use this as an auxiliary information to select kids for and drawing blood sample, and hence estimating the bilirubin level. This will be clear once I'll talk about like how exactly a rank set sample is collected. To collect a rank set sample, this I'm showing like from the theoretical aspect. Like initially we can talk about, this is an hypothetical SRS unit, I mean SRS sample, and this hypothetical SRS sample is actually used in practice to correlate the auxiliary variable with the variable of interest and get the observations on the variable of interest from a smaller number of experimental units. So the procedure is like this. So initially an SRS meaning simple random sample of k units is selected from the population and rank ordered on the attribute of interest. So rank ordered on the attribute of interest, this is actually done through the auxiliary variable. For example, in the previous case, the yellowness is the auxiliary variable. So there may be like only 3 ranks, 1, 2, and 3, 1 for low, 2 for medium, 3 for high. And accordingly, the observations, meaning the kids will be ranked, and then the next step, in the next step, rank set sample, meaning the ordered judgment order statistics would be measured. So what is that? The unit is judged to be the smallest in this ranking, is included as the first item in the RSS. Meaning once, like we'll just think of 3 kids at random, and in these 3 kids particularly, if we are ranking them as like 1, 2, and 3, So 1, 2, 3. Based on this, like we'll first select only the X ordered one, meaning the smallest order statistic for the variable of interest. Then meaning in that case, the one who is having lowest bilirubin level. How do we identify without measuring? By looking at the yellowness of the skin. So that kid will be taken for the sample. In the next set of 3 kids, we'll go for the second ordered statistic. And in the next, in the third set of the kids, again of 3 kids, we'll go for the highest order statistics. So this becomes like, a set size. And from each set, we are computing 1 order statistics. So, and cycles. So how many cycles we are going to do? So this is one complete cycle with a set size of 3. So let me formally talk about it. So following the selection of X ordered one, a second SRS, which I already just told, and similarly the third one, and this process will continue until we reach at the desired size. Basically, if we are having a set of K units in the initial part, that means like meaning in the set particularly. So if the set size is K, then we'll go for K square units in the initial sample, from which we'll identify 1 order statistic at a time. So in the first set, first order statistic, second set, second order statistic, and so on in the kth set, kth order statistic. So that finally we'll get K samples. So this is a single cycle of rank set sampling. But we may not be just interested in K sampling units. We may need some M sampling units. Then we can go for M cycles, wherein K into M is your M. So the same process is repeated for M number of cycles. And then we get like N equals to K into M number of units as a rank set sample. I'll show you pictorially like how exactly it is, but the descriptor which I was talking about, like over here, the auxiliary information plays a vital role. If the auxiliary information is not highly correlated with your variable of interest, then the judgment ranking may go wrong. So it is usually desired that your judgment rank should not be more in number, because ranking them on a larger scale would again introduce error. Like saying that something is small, medium, or large is better than say than ranking the same unit on a 5-point Likert scale or a 10-point Likert scale. So it is better to have a smaller set size. That is the usual practice, so that your judgment order statistics will be accurate. Since here we are talking about we are collecting those many judgment order statistics, those many sets we have, or set size, this is actually a balanced rank set sampling. Of course, there are so many versions of rank set sampling: balanced, imbalanced, perfect, imperfect, and so on. And still there are other versions of rank set sampling coming over. I shall just focus more on the basic version of RSS. So at the end, you will see like from the first cycle, you can see this is the first judgment order statistic. This is second judgment order statistic from the second set, so on. Kth judgment order statistic from the kth set. And this is for the first cycle. So cycle 1 completes. Similarly, we can have like M cycles. So finally, we'll get all these units in the sample. So so that the total number of units will be K into M. And that we are denoting it by N, small n, sample size. Let me motivate like the use of rank set sampling from an example from I can call it as a chemistry or physics, or like it goes in both, I guess. Experts may they can throw some light later. So this is a situation wherein environment is being affected because of the unburned carbon compounds which are present in gasoline. This is a situation from United States. So they actually were bothered about like how these unburned carbon compounds, particularly hydrocarbons, they are affecting the ground level ozone and smog levels. and they actually found out like the main reason for increase in level of these hydrocarbons in the environment is gasoline, and because of that they were like more interested to make this gasoline in meaning modify this gasoline in such a way that the released hydrocarbons would be lesser in amount. So basically they wanted to make this gasoline less volatile, because of its volatile nature, these hydrocarbons would be released in the atmosphere from the tails of the automobiles which are roaming in and around metropolitan cities in US. So they actually modified this gasoline, and which was actually thought to be less volatile in nature, but they didn't I mean, they actually wanted to check whether the standards for this gasoline, whether they are maintained by the concerned outlets in the metropolitan cities. So the outlets for gasoline, like petrol pumps in India, you can say gasoline is a fuel for automobiles, just like petrol and diesel in India. In US, gasoline is used, which is of course having less emission of carbon compounds as compared to petrol and diesel. But still, the emission results in increase in level of smog and other hazards in US. So whether the levels of these released unburned hydrocarbons, whether they are in control, whether the outlets are using the proper gasoline for fueling the automobiles which are approaching their outlets, that has to be checked, and for that a test is being made. The test named ride vapor pressure, in short RVP. So RVP has to be measured from the gasoline samples. Now the problem with the measurement of RVP is, like, a crude measurement can be immediately found from the fueling station, that is outlet itself, but that is a crude estimate of RVP. And RVP tells us, like, this crude estimate, or you can call it as a field estimate of RVP, can of course give us an idea like how much RVP this gasoline has, and whether the by the fueling stations or not, that can be judged from that. But actual RVP needs to be tested in a full-fledged laboratory. Okay, so now the when this checking has to be done, this crude estimate may not be good enough, and one needs to go for the actual laboratory estimate. But the problem with the actual laboratory estimate is the cost. Not because the measurement of RVP in laboratory is costly. The cost is because the transportation of the sample in a proper way, and of course preserving the sample, because it is concerned with pressure and the gases form of that meaning the because of its volatileness, this gasoline, when it is transferred from the outlet fueling station to the laboratory, there is a chance that it will vaporize, and there may be a change in RVP because of transportation. So again, by the time the sample reaches laboratory, one may not be able to again estimate this RVP accurately even in the laboratory setting. So what can be done? If we think of like having a laboratory nearby every petrol pump, that's not possible. So what can be done? Like, facilities are there now. We can see, like, there are facilities which are costly in nature, which can carry the gasoline from the fueling station to the laboratory, but they are costly. So to reduce the cost, what can be done is, like, a less number of samples can be dispatched from the fueling station to the laboratory. But how do we make sure that the estimate is accurate enough? What about efficiency in the estimate? For that, rank-set sampling can be done, and the auxiliary information could be the field values of RVP. So field values, which are the crude measurements of RVP, which are available on the outlets or gasoline outlets that can be used, and then further the same can be used to judgment order the gasoline samples, and then further carefully select the samples for further laboratory evaluation of the RVP. And then one can definitely make a statement whether the standards are met or not. So this is an example wherein we can see like the set size of k equals to 3 of 12 gasoline samples is actually decided to be sent, because based on these 36 gasoline samples one can just get the judgment order statistics which form a rank set sample, which are 12 in number. So just 12 observations could do instead of 36. So this is the complete sample which is enumerated over here, like sample number and the field RVP values, out of which only the 12 values will be sent based on the judgment order statistics. So this is how it is done. Like just imagine all these 36 values are placed in this way, like set size is 3 and the number of cycles is 4. So we are having like 4 into 3, that is 12 number of sampling units. So this is a simple random sample of field RVP values from which the first order statistic is selected. This is the first order, the smallest of these 3 is selected. Then the second one is the second yeah, so this is the yes, 8.17 and 7.9. So based on this, like you can see the first order statistic, then second order statistic, then third order statistic will be selected, and then the finally you will get the value. So you can see like from each cycle we are selecting first, second and third. Okay, and finally we will go on like repeating the same things for 4 number of cycles, and then the observations will be selected for the further analysis. Of course, these are not the observations which are sent for the laboratory, but the corresponding samples will be sent for laboratory evaluation. Now let us see like what is the theoretical development in this, and then we'll propose the new method. I know I'm running out of the time, but already the earlier session was delayed, so I can have.
So, sir, hello, you may extend 10 minutes, sir.
Yes, sure.
Okay.
Thank you. So, so the theoretical aspect of this rank set sampling was given by Dell and Clutter, as I said earlier, and the estimate of mean based on rank set sample was found out, and its variance was compared with the corresponding variance of simple random sampling, and we can see that the estimate of mean obtained based on rank set sample is much superior than the simple random sample. Further, now let us talk about the two sample location problem, which is actually the problem of interest over here, wherein we are comparing the mean. Of course, this is in a non-parametric sense, so I shall say like locations of two distributions whose population distribution is not known, but we have samples from two different samples, and we are interested in checking whether the location parameters of these two distributions, they are same or not. So the theoretical aspects you can see on the screen, like we are putting x bracket 1j so on x bracket kj to be a rank set sample, of course for set size k and m cycles, from a CDF, that is cumulative distribution function, a capital F, and a corresponding y sample from the population, say G, where G is a CDF of the random variable, corresponding random variable. But the difference between F and G is that G is actually written as like F of x minus delta, where delta is a shift in the location. So delta can be treated as a shift in the location. So whether location is same or not, meaning both the distributions are same in all aspects S except the location. That is what is meant by this equation, that is g of x equals to f of x minus delta, for delta in minus infinity to infinity. This tells that g and f are same in all aspects except there is a shift in location. So the target is to test whether the null hypothesis delta equals to 0 versus delta not equals to 0. So this is a standard two sample location problem wherein we are interested to check whether the two distributions agree for location or they don't agree with the location. For this, we can see like the empirical CDFs are denoted by F, M, K, and G, N, Q for the corresponding distributions. So if we look into the literature, a lot many methods you can see which are now being developed for testing these procedures. But if we give more focus on the non-parametric aspects, these are parametric procedures, I will say. The non-parametric aspects, non-parametric procedures, if we see only one procedure is available for testing this problem, this hypothesis, and that is actually given by Bone and Wolf. And that Bone and Wolf procedure is actually nothing but a rank set sample version of the Mann-Whitney test, which is based on simple random sampling. So Mann-Whitney test in simple random sampling is converted into its rank set sample version, and this was done by Bone and Wolf, and hence named after them as Bone-Wolf test, or simply Bone BW test. So of course I shall skip this. I'll move on to this one. Move on to the tests like Bone-Wolf test. You can see over here it is Mann-Whitney U test. It's a statistic based on the rank set sample. Further, it was shown by Bone and Wolf that the sampling distribution of this statistic is distribution free, and hence it can be it enjoys the similar properties as Mann-Whitney U test in your simple random sample. So the decision is made based on the BW statistic obtained using this formula, and it is usually rejected for it is a two-sided. You can have a two-sided region or one-sided region depending on your interest, meaning what is the alternative, and accordingly you can make the decision whether to reject the null hypothesis or not. So similarly, we can see like there can be perfect sampling, perfect ranking, as I already told, in the balanced situation. So perfect balanced rank set sampling. The estimators of the location of the distributions in a robust way were given by Hodges and Lemon, and you can find these estimates mentioned in Bone and Wolf paper as well, wherein the estimate of the location is given by this formula. So del 2 given by this formula, median of this sample minus this sample. Similarly, we can have another estimate given by Hodges and Lemon, which is available in Lemon in 1963, given by this formula. These estimates of location can be used for testing purpose in a simple random sampling, and this was done by Fried and Dehling by scaling these two estimates of location appropriately using this S1 and S2. So Fried and Dehling essentially proposed tests for location based on simple random sampling, based on the scaled versions of Hodges-Lemon estimators, scaling done by S1 and S2 given on this slide. So ignoring the technicalities of the equations and all, the proposed estimator, you can see a proposed test particularly based on the estimate of the location is this particular formula you can see. Now what we do is we convert the simple random sample version of Fried-Dehling test or Fried-Dehling estimators into rank set sample estimators, and further we use them for testing the hypothesis of two sample location problem. And if we compute our Fried-Dehling statistic for rank set sample using this formula, then the test procedure is to reject null hypothesis for large values of absolute FD. Here you can see if we work out the combinations for J, of course K and L, if we change here, we'll get 4 different versions of the statistic. So named as FD1, FD2, FD3, and FD4. So all these 4 versions, they are competitors for the simple random sample version of FD statistic for the rank set sample. An important aspect of this FD statistic or FD test is that it is robust and non-parametric in nature. It doesn't assume any distribution for the samples from where they are coming. So we actually converted this FD SRS statistic into FD RSS statistic and studied its properties, and we could see that it is a location invariant statistic along with being symmetric about the point of symmetry. Usually it is happening to be 0. So whenever the sample sizes are equal, it is happening to be following these properties, particularly location invariant and symmetric. Further, whenever we want to use a particular statistic for testing locations, it is important that the statistic should be location invariant, and then only we can use it for testing location. So once we have defined these statistic, it is important to check whether it is really performing in a better way in all sorts of situations or not. For that, we conduct Monte Carlo power comparison study based on simulated data. So we simulated data 10,000 times, meaning we had like 10,000 runs of simulations for each combination, like set sizes and cycles. Of course, we had two. So, and we used nominal level of 0.05, and we considered different distributions for the data from which data is coming, like normal, exponential, Pearson type 3, which is a skewed distribution, Cauchy, which is a symmetric with heavy-tailed, Pearson type 2 is another heavy-tailed distribution, uniform, a heavy-tailed distribution, double exponential, a light-tailed, and logistic is again a heavy-tailed, light-tailed distribution. So like this is kind of a mix of all sorts of distributions, natures of distributions, and we'll see like how the proposed test performs. So that was the situation for perfect balanced rank set sampling, and this is a simulation design for imperfect balanced rank set sample with distributions limited to only normal, exponential, and uniform, because for other distributions working out imperfect balanced rank set sample is not possible. So let me show you the results of the simulation. Yeah, visible, I guess now. So this is a table which is when del equals to 0. This essentially is a situation wherein there is no change of location, and both distributions are having same location. That is what it essentially means. And the powers, Monte Carlo powers, are reported in this table corresponding to every distribution which we considered for the simulation purpose. And we can see the nominal level which we have fixed, that is 5%, is achieved, which is desirable in these situations. So you can see like FD1, FD2, FD3, FD4, these are the proposed tests, and BW is the only competitor available in the literature. And you can see it is a conservative test, and it doesn't rejects the null hypothesis. Okay, so it is like it is not achieving the nominal level, whereas our procedure is more close, meaning it is providing more close values for the powers, which are close enough to the nominal level when there is no difference. As the difference in locations increase, we can see the power also increases, and it reaches 1 for it is increased, you can see, throughout, and it is higher than the existing method, which is based on rank set sample itself, and it beats the existing procedure in all the aspects. So the similar computations have been done for a different simulation design, and similar results are obtained. So you can see table 3 giving similar results, table 4 also giving similar results for different combinations of N1, N2, M1, M2, and R1. And yes, even table 6, this is for imperfect RSS. So we have like 8 tables over here, 4 for perfect and 4 for imperfect. And in all the situations, you can see, except a few wherein normality is there. Normality sometimes like you can see over here, for del equals to 1, they are competitive. You can see it's not much different. FD2 and bone wolf, they are more or less having same power. So as such, we can see like this fried dialing is a more robust test, and is an attractive alternative to the existing bone wolf test given by based on this Mann-Whitney test of SRS. Just to illustrate our procedure on a real data, we consider the data reported in Moon in 1990, which is actually concerned with the stress of effect of stress on blood pressure of males and female human beings. So data consists of heart rate and weight. They are two separate variables, and we treat them marginally and not as a bivariate data. So we have 36 observations on females and 28 observations on males. The problem is to test whether there is significant difference between mean heart rate and weight of males and females, meaning mean heart rate of males and females, whether there is any difference, and mean weight of males and females, whether there is any difference. So to compute the critical value, we used permutation test, and permutations were done for 1 lakh number of times to compute the p-value for the current data. After computations, we could see like based on the proposed test, which highly rejects the null hypothesis, inferring that heart rates are different for males and females. And similarly, we can see for weight also it highly rejects. Whereas bone wolf, it also rejects, but the strength of rejection is lesser as compared to the fried dialing test based on rank set sampling, which we have proposed. So to conclude or to sum up, the proposed procedure are purely non-parametric in nature, and they are advantageous than the existing procedure, which is a bone wolf test, and they are also they can be considered as an attractive alternative whenever the distribution is symmetric as well as skew, whether it is symmetric or skew symmetric in nature. And of course, the RSS version of this proposed statistic is location invariant and symmetric about the point 0, particularly in practice. These are some standard references. Thank you for your patient listening.
Thank you, sir.
Over to you, sir.
Thank you. So, Dr. Deepak Sakte sir very nicely explained the concept of non-parametric test based on ranked sampling. So usually we have the random set sampling or ranked set sampling. He has also illustrated the concept by using the examples like measuring bilirubin levels in the blood samples of the kids. They also discussed the problems like analysis of RVP in gasoline. So we see that the statistical methods are very important. We can have the huge data around us, but the analysis of that data is very important. And the analysis of that data is very important. and it can be done by using various statistical methods. Sir has explained one of such a method like ranked set sampling method, and he suggested that the accurate results are possible if we consider the small test size. He also explained the various mathematical concepts in between. But after all, we see that the analysis or inference which we draw from that data depends upon which method or which type of sampling method you have used in that analysis. So thank you very much, sir, for giving a very nice informative talk in a simple and lucid manner, even though I am the physicist, but I have got a little bit knowledge from your lecture. So now the topic is open for the questions. So if anyone has to raise the question from the audience, please unmute your mic and ask your question.
Thank you very much, sir.
Anyone from the audience, if asked a question to Dr. Sakte sir, please unmute your mic and ask the question. So I think no one is asking the questions. So Sakte sir has made the ideas very, very clear. And we say
it may be other way around also. That's what I feel whenever I talk to an audience which is not from statistics background. This is the major fear which I have. Like whatever I'm telling, whether they will capture it or not.
And whenever we write a numerous formulas, it again makes it very difficult to understand. So even though they got some idea about how one can do the sampling, various methods of sampling, how we can draw the inference by that sampling. So I think the statistics is very important in this point of view, because there are a number of problems around us, and to draw the conclusion about those problems by collecting huge data, and from that huge data you have to select some of the data, and from that you have to draw the inference which will be very accurate. Even though we do the analysis in practical work, the whatever inference which we have drawn by using the statistical sampling methods, that again it matches with the practical data. That is the beauty of these statistical methods. So now, sir, I am very much thankful to you for giving a very nice lecture on this topic. You have spared your valuable time with us. You have accepted our invitation and have joined this session at the right time. Thank you, sir. Thank you very much. So,
thank you once again.
Hand over to Prachi madam.
Thank you, sir. And thank you, Dr. Sakte sir, for sharing your great knowledge with us. Now, to deliver the vote of thanks, I invite Dr. T.S. Kurne madam, the assistant professor from Department of Statistics.
Thank you, madam. I conclude the last session, the second day, by expressing a vote of thanks. Firstly, I thank the resource person of this session, Dr. D.M. Sakte, sir, Associate Professor and Head of the Department of Statistics and Applied Mathematics, Central University, Tamil Nadu. He waved or shared very well the concept of non-parametric test based on the rank set sampling. Next, I heartily thanks to the chairperson of this session, Dr. Vivek Illedar, sir, Vice Principal of the R.C. Shaw College, Kolhapur. Thank you.
Thank you, madam. Ladies and gentlemen, let's break for lunch. We'll be come back sharp by 2:30 p.m. For the validatory function.